today I'm going to focus mostly on on-chip networks, which is an interesting area that I think will become important going into the future as we scale chips to larger and larger widths and depths and lengths, let's say, in 3 dimensions. And I think this is already happening. As you know, there's a wafer scale chip by Cerebras that is huge, right? And interconnects become a problem over there. Although they're using it as a machine learning accelerator right now, so they're relying heavily on the compiler to partition the code across the chip so that communication is as minimal as possible, but there's still some communication. And then there's the 3D stacking technologies that will increase, I think, the importance of the interconnect going into the future. It's also interesting to note that there's always this debate sometimes in computer architecture. Where is the bottleneck? Is it the computation? Is it the memory? Or is it the interconnect? And clearly, everybody rules out computation today. It's not a big bottleneck. We know how to design compute units. We just need to make them scale to larger, let's say, bigger computations. And we're working on that, but energy is a problem over there. But fundamentally, computation is not a big bottleneck today. But memory and interconnect, this is always a cause for debate, basically. What is memory? What is interconnect? Then you get into the fundamentals of what's the difference between them, right? If it turns out, if you look at memory, it's dominated by interconnect also internally. Remember the DRAM lectures where we talked about reducing latency? It was about reducing the interconnect delay, right? So these things are very tightly coupled. There's a memory technology and there's interconnect technology. And today, you can call this as the communication or data bottleneck, right? And they both contribute to the bottleneck in the end. So you cannot easily say, oh, it's the memory that's the bottleneck. We forget about the interconnect. It's the interconnect that's the bottleneck. We forget about memory. That becomes a bit meaningless after some point. It's really both at the same time. But I think what we know for sure is that we know how to do computation really well. There's still a lot of focus on computation to make it efficient, but compared to memory and interconnect, we know how to do computation really well. Okay, with that backdrop, let's jump into on-chip networks. But before that, I want to finish what we were almost about to finish last lecture. Recall we were talking about the basics of interconnection networks, and we got into a lot of detail actually in topology. These are 3 big things in interconnection networks: topology, routing, buffering, and flow control. Right? We discussed a lot of approaches to this. And at the end, we were talking about buffered flow control. So I'm going to finish that buffered flow control a little bit. Remember, we were talking about evolution of buffered flow control over decades, store and forward networks, which had huge buffers that had to buffer entire packets. And people shrunk the buffers, reduced the latency by essentially coming up with wormhole routing, dividing the packets into smaller flits, flow control units, and managing buffering and flow control at the flit level as opposed to packet level. That is the big innovation going from store and forward and wormhole. And then we discussed the head of line blocking issue even in wormhole flow control, where basically, because you have buffers that are full, some packets cannot proceed, even though their output ports are free. And you can solve this problem with virtual channels, right? If you remember. I'm not going to go through the virtual channels again, but hopefully you remember the idea that virtual channels give you more freedom in scheduling from the flits that are available to you. Whereas if you have a single queue, you just look at the queue, and if that packet that is at the head of the queue cannot go to its productive output port, no other packet that's inside the queue behind it can go to its productive output port. And virtual channels allow you to enable multiple queues and look at the heads of multiple queues and do the scheduling more freely. Hopefully, you'll get packets going to their productive output ports if you look at multiple queues. And we said that you can even complicate the router by making everything out of order, like always look at all flits and do out of order scheduling, but that's additional complexity that no one wants to pay at this point. Okay, and then this brings us to if you're doing buffered flow control, then you need to somehow communicate the buffer availability to the routers around you, right? So that you basically do the flow control, so that the routers can do the flow control for you, right? And there are 3 methods we were discussing. We'll very briefly go over this because it's going to be important to the complexity we're going to try to eliminate by making the network bufferless, let's say, or less buffered. And we talked about credit-based flow control, on-off flow control, and ACK-NACK flow control. And they're all similar, I think, in terms of their complexity. They all have issues, basically. Credit-based flow control, you have an upstream router when it wants to send a request or send a packet to the downstream router, it knows how many buffers are available in the downstream router. And based on that information, it decides whether to send or not send. That's the flow control, right? It's controlling the flow of packets to the downstream router. And to be able to do this, downstream router needs to pass some information to the upstream routers that it could receive packets from. And this is done with credits in this particular case. And this leads to significant signaling. I call this back channels, basically. You have a channel that transmits the packets, and you have the back channel that transmits the credits to tell other upstream routers whether you can actually send the packets on the channel. Yeah. And especially if you have a lot of flits, like small flits, then you have large overhead in this upstream signaling. And we will talk about on-off flow control. That's another way of doing it. And then there's ACK-NACK flow control. You can basically optimistic. You can think of this as pessimistic. These two are pessimistic ways of dealing with flow control. This is an optimistic way of dealing with flow control. Upstream router basically assumes that you have some buffer and sends. And if that's not true, the downstream router knacks. And of course, if the downstream router knacks, you need to keep the packet to yourself, which means that you cannot deallocate the buffer until you receive an actual acknowledgement from the downstream router. As a result, this inefficiently utilizes buffer space. But maybe it's a little bit, yeah, still there's some upstream signaling, right? ACK-NACK. Okay, let's take a look at credit-based flow control. So this timeline is going to be important because it's going to cause us delays. So if you look at node 2, that's the downstream router. Node 1 is the upstream router. Node 1 is sending requests to node 2. Let's say node 2 sends a request to its downstream router, and it flits the parts of the router, and then there's a credit signal sent back to node 1. Now node 1 knows there's some buffer availability in node 2. It does some processing of the credit, and then it sends its flit to node 2, and then it sends a credit back to its upstream router. And then node 2 basically processes that flit. At this point, node 2, so if you look at this picture, node 2's buffer actually became available here, but node 2 couldn't receive a flit. Well, couldn't actually, yeah, receive a flit into that buffer until this point. So there's a delay between when the buffer becomes available and when the buffer is filled. And that's really the credit round trip delay. This is overhead essentially because of that overhead, because you need to communicate the availability of the buffer to upstream routers, you're delaying your buffer allocation, right? Basically buffer utilization goes down because of those delays. Also, if you don't have enough buffers, now your performance goes down, right? If you don't have enough buffering in the node 2, you have some, basically upstream router will not be able to send you enough flits, even though it may have flits available to send, right? Okay, so basically this is the time between when the buffer empties and next flit can be processed from that buffer entry. That's the round trip delay, credit round trip delay. And it leads to significant throughput degradation if there are few buffers. You can imagine this. And usually you need to put enough buffers so that you can tolerate this round trip delays. Okay, I'll just say that much. Okay, let's talk about on-off. This is one method of flow control, of course. This is heavily used actually in existing systems. For example, existing multiprocessor, Cray T3D used this sort of flow control. On-off flow control is another approach to it, but it also has its own problems. Basically, in the end, you're inefficiently utilizing your buffers, yes?
How does the credit system work if there's multiple outputs? Like, do they all get a credit signal?
Exactly.
And all answer?
Yeah, you need to be careful, basically. I mean, you normally, if you talk about a two-dimensional mesh, that doesn't exist, right? You have one link from your neighbor and yourself. But certainly, there are other links coming from other neighbors, and you need to send credits to them as well, yes.
It'd be possible for like one credit to correspond to two fills, which, like if both upstream nodes answer the credit with a fill, wouldn't the buffer then eventually overflow? Because the number of credits doesn't match, like it sends one credit, which matches one space, but actually gets two fills.
Yeah, well, you should not design your protocol such that it's wrong that way, right? You should, yeah, basically you need to ensure that the credit corresponds to one buffer space. And normally how it's done is if you have north, south, east, west routers, for example, in a mesh, you have input buffers for each of them to simplify the credit. But if you have one global buffer and not input buffers for each of them, then you need to actually partition that buffer between your, let's say, upstream routers. And you need to be correct, basically, when you're doing that. And that requirement for correctness actually also potentially inefficiently utilizes your buffer space again, right? Because you need to account for the worst case where all of your upstream routers are sending you flits and send the credit to either one of them. If you have one buffer space available, for example, what do you do, right? Who do you tell to send something to you? But I think that problem is solved easily, easily, at the cost of additional buffering, I should say, if you actually have buffers per upstream router. And in a mesh, you can easily do that. Make sense? But I think you're pointing out to a very interesting problem. All of this increases your buffer size, basically. Okay, so on-off flow control, let's take a look. Downstream router receives a flit. And basically it says, I have a threshold that I reached. If I receive more flits, I'm going to overflow. So it basically tells node 1 to stop. But node 1 did not stop earlier times. So it basically sent a lot of flits. And when node 1 actually processes that off signal, then it stops. This means that you need to set your threshold to prevent flits arriving before this time 4 from overflowing the buffers at node 2. Right? So there's some time for you to communicate the off signal from node 2 to node 1. And during that time, node 1 actually be sending you flits, meaning that that off signal should take into account the worst case number of flits that can be sent during that communication time, right? This again, inefficiently utilizes your buffer space, right? You need to increase your buffer sizes to take that into account. And then after that, you send flits. And then you have another threshold where you actually turn on, you say, oh, I can now receive flits safely from my upstream router. And then you keep doing that basically. This makes sense, right? Hopefully. But you can see that, so the F1 threshold is set so that node 2 does not run out of flits between this time frame also. I mean, it's the corresponding thing basically over here. You should make sure that you never run out of buffer space for flits because there's some communication delay of the off signal as well as the on signal to the upstream router. And the upstream router can be sending flits because it didn't receive that signal by that time frame, right? Okay, so you can see that regardless of however you do, I'm not going to do the NAC flow control because it's going to be similar. But regardless of however you do the flow control, you need to take into account multiple things. First of all, you should never overflow your buffers. Second, if you actually under provision your buffers, then what happens is you have these delays, credit round trip delays that is dominating your execution time. So otherwise, some upstream routers could have transferred the data to you, but they cannot because you don't have buffers available. And that communicating buffer availability actually takes a lot of time. And you don't have buffers available to actually buffer the flits that could be sent while you're communicating that buffer availability. So basically, these are the headaches of buffering, I call it. Yes.
So the gap between F on and F off is what the inefficiency is, right?
Exactly, yeah. So, well, not the gap between them. F off is by nature inefficient, right?
Okay, yeah, okay. We have some pieces of the buffer that we want.
Exactly, you're not using a piece of the buffer basically because those flits may never be sent to you, and you have a large buffer now.
So is this a problem in reality? I think that the amount of reserve space you'd need is probably like latency times throughput, and at the chip scale, I would imagine the latency is so low that it shouldn't matter to wait for one packet.
Well, it depends, right? In the end, it depends on your access pattern, how much injection there is into the network. We will see. We'll answer that question from a workload empirical perspective later. Yes, this is a real problem in real life. Yeah, we will answer that question. But if you're, for example, heavily loaded, you can see that this could matter, right? You need a lot of buffers to digest the traffic that's going into the network. Then this could be a problem. But in real workloads, how often is this a problem? That's a good question. Yes.
Yeah, I'm not sure if this is the same as the previous question, but I don't like if sending the F off would be as simple as sending a single bit. I don't see how sending that single bit can take longer than sending entire flits, multiple entire flits.
Yeah, that's a good question, basically. It depends on your network. And it depends on how many places you're receiving this from. Yeah. Yeah, but I mean, that's a good question also, right? How many flits can be sent while this is happening, right? Uh-huh. Yeah. But the bandwidth for the data network can be higher, right? Yeah. I mean, there are some proposals where you can send multiple flits to multiple packets at the same time concurrently to your routers, other routers. Yeah. I mean, there are a lot of proposals actually, like compressed packets. If you compress packets, maybe you can send multiple of them. If your packets are all zeros, for example, you can compress them easily. And you can have special encoding. Yeah, so there are scenarios in which this can happen. But yeah, again, is it the common case? We'll answer that question later. Okay, so before we go into on-chip networks, I want to spend some time on interconnection network performance. And this is the curve that we had looked at in the past, if you remember. And this is one way of looking at interconnection network performance, right? This is called the load latency curve. And on the x-axis, you have some measure of how much load you have on the network. It could be the injection rate into the network on a per router basis. It could be the overall injection rate into the network. It could be the fraction of the network capacity bandwidth, let's say, that's loaded at the point with some way of measuring that, right? Because you have some total capacity that you can have in terms of buffering and the links, and then you have that what fraction of that is utilized, for example, at a given time. And the y-axis is really the latency. And latency can be measured in terms of average latency of packets, maximum latency of packets, and of course, you can have a latency distribution also. And usually the curve looks like this, basically, as we discussed, because here you're very low loaded. You don't have any injection to the network, so you have some latency. That's your minimum latency. And here you're very highly loaded, such that you've saturated the network. This asymptote over here is really called the saturation throughput. Basically, your latency shoots up, and this is the throughput that you cannot reach, basically. That's where you asymptote at. Make sense? Okay. So then the question is, of course, what affects this latency, right? Let's take a look at the latency part. So there's a minimum latency given by your topology, right? And this is very much depend on the diameter of your topology. Now I'm throwing a term at you. Diameter is the maximum distance, right, in a topology. So if your topology is nicely and richly connected, such that the latency between any given node to any other given node is, let's say, 1 hop, and 1 hop latency is very small, that's a very low diameter network. And your latency or minimum latency will be small to begin with. But if you look at something like mesh, we recall that we said the latency, average latency is square root of n, right? So basically, minimum latency is very much dictated by topology to begin with. So this is why people actually look at low diameter topologies. Can we reduce the diameter of the topology as much as possible without, of course, increasing the cost significantly? Ring, another example, right? Ring, the minimum latency is ON, and it's not very good. And you can do the calculations to get the exact latency. And again, I should say that this picture is very much dependent on the access pattern, right? The access pattern, you assume it could be synthetic, as we discussed last time, uniform random injection, for example. It could be a real workload. You run the real workload and you draw this curve. So it could be, I mean, you could do it analytically also, but you need to assume an access pattern even if you do it analytically, right? So this is very much access pattern dependent. But there is minimum latency given by topology for a given access pattern in the end. And then on top of your topology, you have a routing algorithm. It adds some inefficiency, right? Your topology may be great. If your routing algorithm is not that great, then you have additional latency. And usually there's some inefficiency in your routing algorithm, right? And then on top of this, you have buffering and flow control. All of the management overheads that we discussed, right, in terms of buffering. If you don't have enough buffers, for example, your minimum latency increases. Even if you have buffers because of the management overhead, your minimum latency increases because basically it takes time to allocate and deallocate buffers, right? And then flow control. So basically this top part of the curve is called the zero load latency. Zero load latency is you don't have any load, and that's the latency you get because of the design of your network in the end. Make sense? So this means that you can actually reduce your latency by optimizing all of these. And that's the case, actually. You need to optimize all of these to actually get lower latencies. Each of them can reduce latencies, but there's some minimum that's dictated by your topology in the end. Okay, on the other hand, on the throughput end, there's a throughput that's given by topology again. Your topology supports some maximum throughput, clearly, because you have some links, and how many links you have dictate your throughput. A ring is not equal to a mesh, for example, and a mesh is definitely not equal to point-to-point connections or hypercube. They have very different connections. And then there's a throughput given by routing. Routing is inefficiency, so that reduces your throughput a bit. And then buffering and flow control reduce your throughput even more. And that's how you get to this, basically these asymptotes at the x-axis as well as the y-axis. Makes sense, right? So if you want to improve, again, your throughput, you need to examine these things to get higher throughput. But again, this is very much dependent on the access pattern. So different access patterns can lead to different kinds of curves, as I will show you. We will not go into a lot of detail, but you will see some of these curves soon. Okay, saturation throughput, we defined it as this asymptote, basically. This is the injection rate at which latency asymptotes and shoots up. Okay, let's take a look at ideal latency. I'll go through this relatively quickly, but I mean, kind of it's obvious, I think, in the end. Ideal latency is solely the wire latency between source and destination, right? So there's some, we're assuming a 2D layout, and you cannot really directly, like diagonally go through the chip, for example, with some links. That's why we use Manhattan distance. So you have some Manhattan distance between 2 points measured along axes at right angles, right? It's called Manhattan distance because the streets in Manhattan, New York, are a grid. It's like, you can think of it as a mesh, right? It's a grid. A mesh is a grid in the end. And you don't normally, you're not able to walk diagonally a street because those diagonals don't exist. I mean, they exist, but it looks like a grid. That's why this is called Manhattan distance. So you basically look at the Manhattan distance divided by propagation velocity of the signal, plus add to it the packet size and the channel bandwidth to actually, because you need to transmit the entire packet. And that's your ideal latency. But this ideal latency has additional overheads because you don't have really dedicated wiring, right? This assumes dedicated wiring between one point to another point. And you don't have dedicated wiring because, well, there are multiple reasons, but long wires are segmented by the insertion of routers. So you have some additional router delay, basically. How many hops you need to travel, how many routers you need to pass through, times the router delay. And then there's some latency due to contention that's just added over here because you may get delayed because routers may be contended, right? So that's your actual latency in the end. Okay, so basically, ideally, your latency should look like this, perhaps, right? As you inject load, your latencies stay constant and your network scales nicely regardless of the injected load. I don't know of any network that supports that, unfortunately. I guess if you do point-to-point where you keep the, but again, you have to somehow segment your wires, right? You have to be at least point-to-point here, but then you should also reduce the delay, equalize the delay, for example. Otherwise, you cannot get to this, let's say, flat curve. So real networks have this curve, basically, because these dominate in the end. Okay, and these are some examples. There's nothing to really analyze over here. I just want to give you examples from one of our papers in the past. And these are beautiful curves, as you can see. Here in this paper, we were evaluating 3 different topologies. This is a mesh, as you can see. It's concentrated mesh because each mesh node actually has 4 nodes over here. And then they communicate through a router. Basically, it's some sort of hierarchical mesh. You can think of this hierarchical mesh. You can make it even. So these 4 nodes communicate with each other through a bus, basically, in this case. This is another topology called flat and butterfly. It actually has dedicated links between each of these, let's say, groups. So it's actually much more costly. You can see the link structure over here. And its diameter is actually lower. And this is what our proposal was. It's called multi-drop express channels. We wanted to have a less costly alternative to this flat and butterfly topology on chip. And the idea is basically, you have these links from basically, let's say, X links as well as Y links. But these links, you can actually drop to each of these locations. So while traveling from right to left, for example, you go through one link, but you use the same link to actually drop to this location if you're sending a message to this location, or this location, or this location, basically. For more analysis, you should read the paper. In the end, we may get to it if you have time. But this is a less costly version of flattened butterfly. But it has some other trade-offs also. There are routing trade-offs, et cetera, flow control trade-offs. But if you compare these three topologies, mesh, there's also mesh over here. There's concentrated mesh, flattened butterfly, MEX, and then routers with double the, I don't remember what these were, so don't, I think these are double the bandwidth. I believe, but I'm not absolutely sure. Right now, I don't remember. But you can see the curves over here. This is uniform random traffic, right? Basically, every router injects uniformly onto the network with some random rate. And these are the injection rates. You can see that. And you can, the point is, there are some topologies that do well for this traffic, but the same topologies do not necessarily do well for this traffic. For example, let's take this MEX times 2. It's this curve over here. It doesn't do well on uniform random traffic, but does reasonably well on bit complement traffic, right? So your traffic pattern is very much determines what performance you get on what topology, because these are the different connections, right? Okay, any questions? And then I think there's one more thing over here to notice. As you scale the topology from 64 to 256, the characteristics again change potentially, right? They don't completely change, but they can change potential. Now, unfortunately, it's not a one-to-one comparison for everything, because there are some additional topologies that we examine over here. But basically, you need to do the performance analysis right to really understand what's going on. And this is just synthetic traffic, right? These are not real applications at this point. I will argue that this is interesting, but maybe you don't care that much about this, right? This is good for understanding the network performance, perhaps. But in the end, you're running real applications. So that's probably what matters, right? That's going to be my argument also going forward. Yes?
So the difference between these kinds of traffic is not the content of the packages, but rather the time distribution and the size of the packets, right?
I don't think there's a distribution on the size of the packets, but it's really the communication. So uniform random is you uniformly pick, so you select any node uniformly picks another node to send messages to at a random rate. Whereas bit complement, for example, I think bit complement, this is one version of bit complement. I think there are multiple versions. So you have a coordinate for the node, right? XY coordinate. You basically complement those coordinates, and that's your destination. And you keep sending to your destination. So it's a much more regular traffic pattern compared to uniform random. Make sense? Transpose, I think again, because these things change also depending on the paper. A router at XY sends a message to a router at YX. I don't know if that's true always, but I believe that's the case. So these are different kind of patterns. When do they happen? Again, you can question, right? Which applications do this? It could happen, actually. Some of these happen. Bit complement is a little bit tricky to justify, but transpose could happen, yes.
So we have
I mean, certainly, right? You can have reconfigurable interconnects that you can configure, or you can have multiple different interconnects that are heterogeneous. One is latency optimized, one is bandwidth optimized, one is optimized for one access pattern, another optimized for another access pattern. So heterogeneity, configurability, and reconfigurability are all applicable to this also. Yeah.
I mean, at the fundamental level, the bandwidth will always be fixed by the amount of physical connections, right? So yeah, how is it possible to have an adaptive topology? Because by the wires.
Yeah, but topology is the wiring that you add, right? Like I can say my topology is ring. Then I dictate the wires by saying that's my topology, right? I can always increase the wires by making my topology bidirectional ring, or a torus, or something else, right? So I can have multiple of those topology in place and then decide which network to inject into. That's one form of asymmetry. And there is benefits to this, actually. We have examined those topologies. If you have multiple networks, you can actually be much more energy efficient and also higher performance compared to a single network. But of course, the cost is additional networks, right? Now you have to operate 2 networks. And then you can also have reconfigurability. You can turn on and off some wires, for example, some links by doing reconfigurability. But in the end, yes, in that case, you're dictated by the wiring capacity, right? Yes.
Injection rate here just means the percentage of total system.
Yeah, in this case, I think that's the case, but it also depends how you define it, basically. It could be number of flits per cycle per node, for example. Actually, I don't remember what was in this case, so you should read the paper. It's been a long while since we actually did the research.
So at just 2% of total load, it starts.
Yeah, that's a good question. Maybe that's not the load. Maybe that's not the total load, basically. Yeah, take a look at the paper. Let me know what it is. Yes.
Right. So, sort of related to the memory performance attacks, is it possible to have an attacker on one of the nodes inject traffic into the network to deny quality of service to other?
Yeah, exactly. I mean, this is something I had mentioned very briefly when we talked about memory performance attacks, right? You can actually do this sort of attacks on the network also, yes. If your network doesn't provide fairness or quality of service, certainly.
Has it been explored before?
Yeah, I think so. Yeah, maybe not as much as it should be, but quality of service aware networks have been explored.
Right.
But yeah, this sort of attacks, I think our paper at Micro 2009 looked at it and examined it briefly. But our goal was to really provide quality of service. Our motivation was that, basically. Okay. And this is the paper, if you're interested, that talks about this multi-drop express channels and also looks at different express topologies. So express, why is it called express? Because you're providing some express channels, right? So if you look at mesh, there are no channels that enable you to communicate between this node, well, this set of nodes, let's say, with this set of nodes. Whereas the other topologies provide express links. So you can go from here to here with an express link. And this topology is a cheaper version of that express link because you can go from here to here with a single express link that can actually drop you to intermediate locations. Okay, let's look at the performance metrics. I think we've talked about a lot of these. Packet latency. There's also round trip latency, request response latency, basically. It's not just one packet, but how long does it take for your request to actually come back with a response, whatever that request may be. It could be a memory request. It could be, I don't know, a coherence request, for example. So there are different request types also, keep that in mind. And a single network may be satisfying those request types, right? You may also have multiple different networks for different request types as well, as we discussed. Saturation throughput, we just defined. But perhaps, I mean, more importantly, maybe we should be looking more at the application level performance, right? Execution time. And system performance, job throughput, which is affected by other applications also, interference. And this is something that we had done. When we looked at a lot of the on-chip networks literature, let's say, at the time we were doing these research, we felt that it was too focused on the network itself. So it's interesting. I think this is an issue with potentially communities, right? So if you can be very focused on the network and you could keep optimizing your network with these traffic patterns. But then the question is, what are you using the network? You're not designing the network for the sake of designing the network. Right? You're designing the network for the sake of hopefully solving a problem in the end, running an application and getting the results. Right? And these may not be interesting in the end to you at all. Right? You can draw all these beautiful curves and they may be meaningless from a user perspective. Right? And that's been our argument for a long time now. So I'm going to talk about that basically. So we should perhaps be focused more on the application level effects of the network and the system level effects of the network, right? You may be running a single application, you may be running multiple applications, and your network should be able to support that, especially if you're running a multi-core system, right? Okay, so this brings us to buffering and flow control in on-chip networks. So I'm going to give you a story of what we have been looking at in this area, if you're interested. Any questions? So there's a lot to cover in on-chip networks, actually, but we don't have time to cover. Maybe I'll point you to some directions. But on-chip networks are interesting because if you really want to have many processing elements and scale them up, you need, you cannot use basically dedicated wires, right? Dedicated wiring actually is quite complicated. We talked about buses are not good. Rings at some point don't scale, but rings are actually an example of on-chip network also, right? We're going to talk about meshes in this case because that's certainly interesting, right? It has its downsides, as we discussed, but buses and crossbars and also rings are not that scalable. So we want to connect processing elements, which can contain cores, L2 banks. Some of them may contain memory controllers with routers that are connected via mesh, basically. And we're going to assume packet switching at this point. And 2D mesh has been the most used topology, actually, in this research, as well as prototypes. So Intel developed this single chip cloud computer prototype. I think it was in 2008 or 9 or so, maybe even earlier, 2006, which was actually an on-chip network. They had a bunch of other prototypes. I think Polaris was one of them. So they were quite interesting research prototypes also. And primarily the function of this on-chip network is to serve cache misses and memory requests, including coherence, etc. Okay, hopefully that's clear, right? And basically, if you remember the router, this was the assumption. A lot of works basically just assume this. We want to have a buffered router and a crossbar, a 5x5 crossbar, basically. And this is the routing logic that you have. You have route computation, virtual channel allocation, and then switch allocation. And these actually make your router more complicated. Basically, this router is actually a pipeline by itself. People were proposing like 5-6 stage pipelines to do the router, basically to do all the tasks associated with the router. And I think it's interesting, certainly. You can make the router much higher frequency by making the pipeline deeper and better. And then you employ speculation, actually. There was a lot of speculation proposals for the router, for example. The router speculates which flit will get which port, or which flit will they go to which port, and then speculatively allocates. But then if there's a conflict, it basically denies sending the flit to that output port, for example. So there's a lot of speculation going on in this pipeline, just like a regular instruction pipeline, right? Instruction processing pipeline that you saw in digital design and computer architecture. And we felt it was a bit too complicated, let's say. But I think it's interesting. I mean, there's a lot of interesting research in the router pipeline. And some of them are actually on the simpler end. How do you simplify the router? Some of them are on the, let's say, how do we actually make the router extremely complex and make it high performance? But before we go into that, let's talk about the difference between on-chip and off-chip. On-chip and off-chip is interesting because off-chip routers, you can make them more complex relatively easily, right? You're dedicating a router chip potentially, right? Whereas on-chip, well, let's take a look at the trade-offs first. Clearly on-chip, you have low latency between the cores, right? It's not like you're communicating between two different chips. There's no ping constraints. This is actually very important. Basically, when you're communicating from chip X to chip Y, you have some ping constraints. So you're very much bandwidth constrained and wiring constrained. So these wires are not very scalable. There may be so many of them, but they're not scalable. They lead to issues that we discussed yesterday. But you basically cannot have a huge number of them. Whereas on chip, you have rich wiring resources, right? No ping constraints and rich wiring resources. Again, you're not infinite because you're limited by the chip area, you're limited by the logic area, and you're limited by the 3D stacking that you can have in the metal layers, right? But still much richer than off-chip. As a result, on-chip, you can have very high bandwidth and also a simpler coordination. So if you want to coordinate like tens of thousands of processors that are far away from each other, then you need to have rich wiring resources potentially as well. Whereas on chip, you can have a single global control unit, usually not desirable in general, but you can imagine having that, right? On chip in one corner, you can have a global control unit, right? Yes, it reduces the distributed nature of a multi-core, reduces the parallelism, but you can imagine having that. But on-chip also has constraints and disadvantages, right? And basically, you're limited by the 2D substrate, whereas here, this is 3D, right? I can even move it, as you can see. I cannot move my on-chip wires. Yes?
How do these wires, do they really look like wires like the one?
Yeah, exactly. If you look at a supercomputer, for example, I wish I could pull up a picture. Well, maybe I'll pull up for the next class. There's real wires. The Ethernet cables, for example, are great examples for this. Some supercomputers actually connect to each other through Ethernet. Yeah. And it's amazing. Basically, there have been bugs because people actually miswired these computers, and they basically took months to actually solve those kind of bugs. Okay, so on chip, 2D substrate limits used to implement topologies. We have seen that yesterday, right? The hypercube topology, for example, how do you implement on 2D? Whereas you could actually do it with this sort of wires, right? It's not easy, but you could do it. Well, if you scale to, I guess, 10-dimensional hypercube, then I'm not sure. It becomes harder, right? But on chip, I think the huge difference is energy and power consumption is a key concern. Because you're very much power limited in the end. And clearly you care about energy of a single chip. So complex algorithms are undesirable and large buffers are undesirable, actually, as we will see. And also, even though you have rich wiring resources, not all your area is dedicated to wiring, right? In the end, you have a lot of logic that you also need to implement. So you cannot easily say, oh, okay, I can put wires anywhere. Right? So your wiring is constrained by logic area and also, also basically your fabrication capability, right, in the end. Okay, so let's talk about some other differences. There are cost differences. So off chip, the main cost is really channels, pins, connectors, and cables. On chip, the cost is really storage and switches. Wires are plentiful. And this likely leads to networks with many wide channels and less buffering. And channel characteristics are also different. On chip, you have relatively short distances, low latency. But still, you need repeaters because you need to preserve the signal integrity, right? But the good thing is you can put logic in repeaters. So on chip, actually, you can imagine a lot of things relatively easily because logic is also extremely cheap on chip, right? And workloads, I think that's also different, right? Off chip, usually people have considered large-scale parallel applications like supercomputing applications with multi-chip traffic, right? Whereas on chip, you have limited kind of traffic. You have multi-core cache memory traffic, right? Yes?
How does it prevent cross-coupling in on-chip wires?
What do you mean, in general?
Yeah, in general. I mean, these are really high-frequency connects, right? So it just seems like there would be so much interference from all the other surrounding wires and the logic.
Yeah, I mean, certainly there's a lot of crosstalk that happens in these on-chip wires. You usually use some sort of shielding, you distance them. There's some distancing rules, right? Yeah. Yeah, but as you scale down to smaller technology nodes and go up to higher frequencies, that kind of crosstalk is important, yes. Yes?
Maybe this is a dumb question because I'm not an electrical engineer, but why are we limited by two-dimensional wires? Why can't we just put a wire crossing over the top of another wire?
Well, you can. In the end, you can, but there's a limited number of layers you can do that with. Yeah. Now, if you go completely three-dimensional technologies, yeah, then you reduce that. And that's happening right now. But there's still time to actually make it really work reliably. Three-dimensional technologies where you can actually put logic layers and interconnect layers and memory layers, and you can mix and match them nicely, will solve that problem, basically, that two-dimensional dependence. But, I mean, we're not there yet. So as we discussed yesterday, you have, let's say, 7 to 10 or 7 to 12 metal layers today, so you can deal with them. But if you actually use those metal layers, you also have different constraints because of what he said, basically. You have coupling between the wires, so you cannot really place every wire everywhere you want in the end. Yeah, if you've taken well, maybe you didn't take a VLSI design class, but if you take a VLSI design class and actually take a serious class, meaning an advanced class where you actually do the layout yourself, basically you have to have these design rules, right? This is called DRC in VLSI design rule check. And you have to obey these design rules. And you may ask why these design rules are there. Well, for example, one design rule is you cannot have a wire within 20, I'm just making it up right now, 22 nanometers of another wire, right? Why? Because otherwise, well, there could be multiple reasons. Otherwise, you could run into reliability issues. The lithography engine may not be able to etch those wires that close to each other because you have a minimum feature size, right? So there may be multiple reasons for this. So you're limited by the fabrication technology also. Okay, these are actually very good questions. So this is an original paper that actually introduced the idea of on-chip networks from a circuit level perspective, let's say. And I would recommend, this is one of the recommended readings if you have looked at it. It's a short paper, so I'd recommend reading it. It's relatively easy to read, it's 6 pages. But let me actually say a couple of things over here. I mean, we've already said a lot of this, but in particular, wires and pins are more abundant than in inter-chip networks, and buffer space is less abundant. So these faults actually realize some of the issues between on-chip and off-chip networks. And these differences enable a number of new network topologies, flow control methods, and other techniques. And they identify 3 areas that are ripe for future research, like what topologies are best matched to the abundant wiring resources on an available chip. They can read this. I'm not going to go through this, but they do some back of the envelope calculations, saying how many wiring that they have at that time of times technology, right? What flow control methods reduce buffer count and hence router overhead? It's interesting that this paper actually realized that these are problems, but there was not that much research on reducing that buffer overhead significantly. So we're going to talk about that research that reduces that buffer overhead significantly, let's say. What circuits best exploit the structured wiring of on-chip networks? This is also interesting because you have, as opposed to some random wires that go long, now you have limited wires and you have modular design. So mesh is a great example for modular design, right? That limits your wire lengths. Now you can actually say, oh, my wire length is limited. You can actually play a lot of circuit level games to actually make that wires faster. Like, for example, they talk about low swing, pulsed low swing drivers, etc., to reduce power dissipation. Whereas it's not easy to do that if your network is not limiting your wire structure. Okay, I'm not going to talk about that in more detail. I recommend reading that paper. We also look at on-chip and off-chip trade-offs compared to the internet. So this is a more application and system level perspective. If I think of this is a more circuit level perspective, design level perspective. That's why it's in a design automation conference. We also wanted to look at it from more application and workload level perspective. What are the differences? Because we know how to design these networks. In a sense, networks are not new, right? Clearly. And we've been designing the internet. And we have a lot of complicated algorithms on the internet, for example. Then the question becomes, how our on-chip networks are really fundamentally different from these, right? And in this paper, we actually look at a lot of interesting things like congestion and scalability. And as far as I know, this is the only paper that networking people accepted to their networking conference. They tend to be very protective of their conference. So I haven't seen any other on-chip paper in this general networking conference. This is a top networking conference, as you can see. Yeah, I mean, we have been looking at this actually. This is the earlier version of that paper that talks about essentially that application level perspective. Okay, so let's take a look at this buffers. So we're back to this curve: injection rate, average packet latency, and this is what you would naturally expect, right? If you have large buffers, you saturate at a higher throughput. If you have small buffers, you saturate at low throughput. And here we're not even penalizing the buffers in terms of latency, right? Small buffers may actually have higher latency to begin with also, but ignore that. So basically, your network can sustain higher throughput if your buffering increases, because buffers increase the total available bandwidth in the network, right? A good way of thinking about it is if you don't have enough buffers, you cannot inject into the network. Clearly, your injection rate is lower, right? So this is good. But buffers also consume significant energy and power. You have dynamic energy when you read and write into the buffers, and static energy, leakage energy, even when the buffer is not occupied, right? And buffers also add complexity and latency. We discussed a lot of this, right? Logic for buffer management, virtual channel allocation. We didn't even talk about the allocation, right? There's also allocation that you need to do, and credit-based flow control. And they require significant chip area also. So there were some prototype chips that were manufactured at that time. This was at UT Austin, TRIPS. It was a multi-core chip, basically, mesh-based. And they basically showed that input buffers occupy 75% of the total on-chip network area. I think on-chip network area was maybe 30, 40% of the chip. And 75% of that was buffered only. And this is an interesting paper also I would recommend if you're interested in reading it. So the question we asked was, can we actually get rid of buffers? Let's take the extreme view and get rid of buffers and see what happens. It's a bit surprising that no one did this, but we want to do it. I guess there are issues, that's why no one did it. So we wanted to solve the issues also. So the question is, how much throughput do you lose? So clearly we're going to lose some throughput, right? The question is how much in real applications. I don't care about those, let's say, traffic patterns. What about real applications? Up to what injection rates can we use buffer, and how much latency is affected, of course. And up to what injection rates can you use this bufferless approach? And are there realistic scenarios in which you can actually do this? Okay, what is the energy reduction that you gain? Can you actually reduce area and complexity? And this is from the presentation of the paper in ISCA 2009, so you can read the paper. But we're going to look at some of these answers. So basically, it's not a new idea. We discussed this idea yesterday, right? It was introduced by Baran as hot potato routing in this 1962 paper. And the idea is deflect the packets. Don't do any buffering. whenever you get a packet, deflect them. Send, if no productive direction is available, output port, no productive output port is available for the packet, send it to another output port. So you're always forwarding all incoming flits or packets. The flits is the granularity of allocation that we're going to assume going forward. Flits to some output port, right? Of course, this works if your input ports, output ports is at least greater than or equal to your input ports, right? If you have a topology where that's not true, this doesn't work. So your topology needs to support it, but most topologies on chip, actually all topologies on chip actually support this that I know of. Okay, we discussed this, right? So let's, I think this is the animation, so I'm going to go through this animation quickly. So what can this buy you? Hopefully, that's the hope, we get rid of these buffers. That sounds nice, because these are actually a lot of buffers. We're going to calculate them later. We're going to calculate the area reduction if you get rid of them later. Hopefully, you get rid of the flow control backwards. You need to have some other sort of flow control. And then, hopefully, you get rid of all of this, right? And you need to replace it with some sort of ranking and port prioritization. And it turns out this is actually not easy. So in the initial work, we didn't realize how hard it was. Once you go a little bit deeper, you realize this is actually going to complicate the router. But you can get rid of buffers. So basically, there needs to be a new arbitration policy if you get rid of traditional way of doing buffering. Basically, there are two parts of this router. One is you need to rank the flits. Why? Because you need to ensure there's no live lock issues, right? Remember, I talked about the total order of flits yesterday. You need to form a total order of flits, and we use the age order. When the flit was injected into the network, it's age. And we basically always prioritize the flit that's the oldest. And that requires a ranking of the flits. And then for a given flit in this ranking, find the best free output port. And you apply to each flit in the order of ranking. Now you can see that this actually serializes. So creating a ranking takes time. And this serializes the output port allocation. And that's going to make our router a little bit slower, unfortunately. Okay, so basically, this is the routing algorithm now. You have oldest first arbitration. We also evaluate other policies, but they're not live lock free. We evaluate them to see the impact of oldest first arbitration on performance. But this is live lock free. I think we already discussed this basically. Well, I guess the specific port prioritization policy that we use is you assign flit to productive output port if possible. Otherwise, you assign it to the non-productive output port in rank order. Makes sense, right? Okay, we've already discussed this. It can be applied to most topologies where output ports, I don't know why this is messed up right now, but greater than equal to input ports. And each router should be reachable from every other router, but that's essentially all topologies that we know of on chip. And there's a flow control. Basically, the flow control now becomes completely local, right? Injection policy. You can inject whenever an input port is free to a router. So you're a local processing element. You want to inject into the router. You just need to detect whether any of your input ports is free and inject into that input port. So there needs to be some detection logic for sure. Yes. And this is, there are no deadlocks because every flit is always moving. In this case, buffering actually leads to deadlocks, but we will see some other sort of deadlock later on in the next work when we go a little bit deeper. And there are no live locks because of this oldest first ranking, actually. Oldest first ranking is provably live lock free. Okay, so let's take a look at advantages and disadvantages of this approach. Basically, you have no buffers on the left side, purely local flow control, simpler, hopefully, no credit flows, no virtual channels, simplified router design, no deadlocks, live locks. We eliminate the live locks with the oldest first ranking. And there's adaptivity. I think this is actually important. Basically, if you have a congested area in the network, you can route around it, right? Naturally, deflecting actually enables you to route around those congested areas. And if you have little congestion, that's actually good. You have adaptive routing for free, let's say, because adaptive, if you think about deflection, it's adaptive routing, right? It's not minimally adaptive, it's non-minimally adaptive, but it's adaptive. So if you can route around congestion. Now, if you're too congested, then you run into those issues over there. So too much congestion is bad probably for bufferless, but little congestion is actually, it shows an advantage of bufferless. You can reduce the router latency. We're actually quite aggressive in claiming that you can reduce router latency. And I still believe that you can reduce router latency by doing more optimizations in this area. And then you can have area savings clearly. So we're going to evaluate some of those. But of course, disadvantage is you have increased latency because whenever you deflect, you're traversing more number of hops, right? Whereas with buffering, you're not traversing more number of hops. You have reduced bandwidth, clearly. You have increased buffering at the receiver. Now the receiver becomes a little bit more complicated because it needs to basically reassemble the packets. If you think about wormhole routing in virtual channel, it's nice because receiver receives the worm flit by flit in order, right? Whereas if you're doing bufferless routing, like we discussed at a flit level, receiver now receives different pieces of a packet at arbitrary times, right? We will see that. And this complicates the buffering at the receiver's end, right? Wormhole is very nice, right? It's very clean. The flit doesn't get reordered inside the network. Whereas right now we're reordering everything about, well, the packet, the flits of a packet don't get reordered inside the network with wormhole. Here, it's arbitrary, right? Because we're doing flit level routing. Okay, of course, doing flit level routing requires you to have header information at each flit. So there's some additional overhead. And all this first arbitration is complex. We're going to quantify that in the next work. And quality of service becomes a little bit difficult also, which I'm not going to talk about right now, but you can think about it. So let's look at the impact on energy. And I guess throughout your latency reduction also, but I'm not going to talk about that. So let's talk about the synthetic traces. So this is synthetic traces. And you can see that the news don't look very good in this case. This is injection rate in terms of flits per cycle per node. And this is, I think, two-dimensional mesh again. You can see there are different policies over here. These are BLES policies, bufferless routing policies. There are multiple policies that we discussed. We actually implemented wormhole routing also. It doesn't work really well. It's a mess basically to support wormhole routing in a bufferless fashion, let's say. You need to divide the worms and create new worms, for example. It's an interesting exercise, but it's too complicated. You can read the paper for that if you're interested. But basically, you can see that there's a huge throughput gap, right? This is the best baseline, minimal adaptive routing using buffers. So if you just look at this picture, you may say bufferless is a bad idea. And maybe it is in some cases, but not in all cases. So we look at some moderately intensive workload over here. And we assume perfect caches because perfect caches actually put a lot more pressure on the on-chip network. Why? Because if your caches are not perfect, and if some of the requests go to the memory controller, then what's happening is your network is not as contended on chip, right? Because some of the requests go out and wait in the memory controller. In the meantime, the core starts waiting because it's waiting for this request. So core is not injecting into the network anymore, unless you have heavy levels of multi-threading, right? So that's the interesting part about on-chip networks now. What are they designed for, right? If you look at a supercomputer interconnect, maybe they're not carrying as much cache coherence traffic, right? Maybe it's more coordination requests, etc. But on-chip networks, I think, are quite different. So you can see that basically, essentially, there is no difference, almost. If you look at this picture, yes, there are slight differences. Y-axis is performance, x-axis is different routing algorithms, dimension order, minimal adaptive, ROM is another adaptive algorithm. And these are BLES algorithms. You can see that they're essentially the same. In some cases, actually, if you reduce the latency of the router magically, which we hoped, you can actually get better performance. So basically, this is a moderately intensive real application, and you're not losing performance, right? Well, I guess 4% performance in the dense network, in the 16 node network. Okay, but you're gaining a lot in energy. So you can see that there's almost 40% energy reduction. So this may be a good trade-off, basically, under some conditions. And you can see that buffer energy reduces significantly. Link energy increases a little bit because now you're using links as the buffers, right? And I think router energy also slightly increases because you're exercising your routers a little bit more. Because every time you send a packet toward a destination that it doesn't want to go to, you're utilizing a router that's not necessarily going to be utilized, right? So overall, energy results also look quite good. So basically, there are multiple reasons, right? First of all, injection rates into the network are not extremely high. So if you look at this picture, you may say, okay, bufferless is a bad idea, but real applications are actually not going toward this direction, it seems. Yes?
Were you also able to characterize why it's so bad in uniform random case? Was it due to the extra headers that you send with each flit, or is actually the throughput bad?
Well, it's mainly because you don't have buffers. Basically, if you have uniform random and if you keep injecting at a high rate, buffers enable you to make progress. But if you keep injecting at the same rate on a bufferless network, what happens is you don't have buffers, so you quickly run out of links, and your links are all full with packets that are trying to reach their destinations, and a lot of them are deflecting. So there's overheads, yes. Whereas if you had some buffering, you would not deflect, right? So your buffers will basically enable you the packets to wait and not congest the network. Okay, so basic injection rates are not extremely high on average on real workloads. That's what we found. And also real systems are self-throttling. Basically, a core doesn't operate in isolation, right? It doesn't keep injecting requests and injecting requests and injecting requests without waiting for the responses. So if the responses are not coming, after some point, the core stops injecting, right? This is the self-throttling effect. Hopefully there's a reason why it's injecting these requests, right? Unless it's malicious, right? Okay, so there's self-throttling effect. And also network links are used as temporary buffers, right? So this handles some bursts and temporary hotspots. Okay, these were our conclusions from the first work basically. We get significant energy savings for a wide range of applications and network seconds. We conclude that buffers are really not needed. And you get significant area savings. These are back of the envelope calculations. We're going to actually make these a lot more clear and cleaner in the next work. And hopefully you simplify the router and network design, and performance slowdown is minimal. And if you're really aggressive, you can increase. So we basically argued that there's a strong case for rethinking NOC design, and future research should really focus on making it real, let's say. And that's the paper. I think that's one of the required papers. How many people have read it so far? Okay, only one. Maybe some people on Zoom also. That's good. I recommend reading it. It's interesting that people have not thought of this a lot, right, in the on-chip network. I think this happens in communities and research sometimes. There's some set way of doing research, and people assume those things. But I think it's good to question some of those things once in a while. And this is one of those papers, I believe, did that question. Okay, do we really need all of this complexity in our networks? Now, of course, the question is, how do you make it real is a different question, right? I think of this as similar to the radar paper. If you remember the radar paper, in the radar paper, we said, oh, do we really need to do the refresh this way? There's a lot of heterogeneity in the refresh rates. But we never really solved the problem. We never made it real at that first work, right? And these works are important because they question a basic assumption, right? Then, of course, the question becomes, how do you make it real? What are the real challenges underneath to basically enable this new high-level idea? So it turns out this high-level idea also has issues, right? So these are some issues in bufferless deflection routing. First of all, live lock. Yes, live lock you can prevent with total order, but at what cost, right? That's the question. So resulting router complexity because of live lock freedom. How do you actually eliminate that if you can? And clearly, at high loads, you will get performance and congestion issues. And can you actually handle high loads also? Basically, very intensive workloads on the network. This is the tough part, basically. You can perhaps solve live lock and resulting router complexity, but this is going to be very hard without buffers, and we will see that. And then quality of service and fairness. I think this is a problem with any network, clearly, especially based on what we discussed earlier in lectures, right? Your memory controller provides fairness, but if your network actually doesn't provide fairness and quality of service, whatever you do in some other part may be useless, right? So this quality of service and fairness are usually problems of weakest link. I like thinking of it that way. So if you have a weak link in any part of your system, it doesn't matter what your other parts do. If they all provide good quality of service, it doesn't matter because you have a weak link here, and that weak link is really deprioritizing one application. That will never get prioritized in some other part where you support quality of service. So you cannot really have a weak link in your system if you really want to have quality of service in your system. Okay, so let's take a look at these issues. And this is the next paper that we wrote on the topic. So basically, our goal was low complexity routers in this case. And you can see this is the summary of the BLESS paper. And these are quite significant numbers. But basically, we did not address the complexities in the router in the original work. There's long critical path, large reassembly buffers. And we basically mentioned them in the paper, but we never addressed them. So basically, we need to obtain these benefits while making the router more practical. The question is, can you do that? Of course, and if you make the router more practical, how much of the benefits still remain, right? Okay, so let's take a look at these problems a little bit more. So live lock freedom, a packet should not be deflected forever, clearly, and you must reassemble packets upon arrival to the destination. Yeah, basically, we've already discussed this, right? Flit versus packet. So this is a bufferless router at a high-level view, as was proposed in 2009. So you have a deflection routing logic, you have some crossbar, and then you have some reassembly buffers on that node. Every node looks like this, basically. And we remember the deflection routing logic. We have the ranking and then the prioritization. So here, you need to provide live lock freedom. Here, you need to provide efficient packet reassembly. So how do you provide live lock freedom? We were sorting the packets by age and then assigning them in age order to output ports. Oldest ones hopefully get the productive output ports that they want. And it turns out it leads to more than 40% longer critical path than a buffered routing. If you actually go and implement this in RTL, with some optimizations, your critical path increases significantly. You can reduce your critical path by exploding the area of the router, because you make some parallel decisions, as we will discuss in a little bit. But that comes at the cost of additional area. And then reassembly buffers are actually quite large. Reassembly buffers must be sized for worst case. What is worst case? Any node can receive a flit from every other node, and that leads to a significant amount of buffering per node. Of course, this scales with the number of nodes you have in the system, right? 4 kilobyte per node may be true for 16. I believe this is 16 node networks, but if it scales with the number of nodes. Okay, so let's take a look at live lock freedom. I think this is interesting because now we're going to also question the assumption of what is really needed for live lock freedom. So what stops a flit from deflecting forever? Right? That's a good question, I think. All flits are time-stamped, and oldest flits are assigned to their desired ports. So you have a total order amongst the flits. It doesn't need to be a time order, right? It could be any order. As long as you impose a total order on the flits in your network, and every router obeys that order, that's good. Timestamps are just one way of doing it, right? You can generate some random numbers, assuming that random numbers are coordinated across all routers where the flits are generated, and everybody agrees on the random number generation sequence. That could be your total order. Makes sense, hopefully. Because our goal is to really get packets out of the network. Our only goal is really to stop a flit from deflecting forever. There could be additional goals, of course. How do you do that? High performance, etc. All this first sounds reasonable, at least, because, well, intuitively, you would say older flits that are injected into the network should go earlier or get prioritized. But we know that there are downsides to oldest first as well, right? Clearly, there are downsides to oldest first in fairness, for example. Okay, so basically, this guarantees progress to the oldest flit, and new traffic is always lowest priority in this case. But hopefully, while you remove older traffic in this order, and then new traffic gets the highest priority. So every packet at some point becomes the highest priority. But what is the cost of this? So let's take a look at this. So essentially, this is 4 flits, and you want to order them. The router must really sort the flits by age. So you have a long latency sorting network. This is a sorting network, which is essentially levels of comparators, right? So for 4 flits, you need 3 comparator stages. Let's look at an example. So basically, this rank order should be here. 1 should go here, 2 should go here, 3 should go here, 4 should go here. So you compare and swap. Basically, that's what we're doing, compare and swap, if needed. Okay, hopefully this is obvious at this point. And with 3 stages, you get the you get the output that's sorted. But clearly, this increases your critical path now. Now, this may not be the worst part of your critical path. Actually, what I'm going to describe next is going to be worse. So after sorting, flits are assigned to output ports in priority order. Now, what does this mean? Port assignment of younger flits depend on the port assignment of older flits. So you have some sequential dependence in the port allocator, right? Because the older flits, by your definition, should get the output port that they want. And then you go to the next oldest flit. It should get the output port it wants if it can. And then you go to get the oldest flit. next oldest flit, and then you need to have a sequential dependence to be able to do this. Let's take a look at an example. So we've already sorted the flits. The first one wants east. That's the only place, that's my productive port. At this point, it gets granted because all ports are available, right? You didn't assign any port to anyone. This is the highest priority. So that's easy. But now 3 ports become available. Flit 2 wants to go to east also. Well, you cannot get it because I made the decision to send flit 1 to the east because it was a higher priority. So it gets deflected basically. Now 2 ports are available for the next decision. It wants south, so it gets south. And now only 1 port becomes available for the 4th flit. And it gets deflected also because south, it also wants south. So this is how you get deflections and grant signals. And this is your sequential dependence. Now you could argue that, oh, why don't you parallelize this and do all the decisions, like enumerate all possibilities and eventually select based on who gets what? That increases the area significantly of the router. Yes, you can do that. It's like if you know about how to design adders, right? You have this carry bit and you have a ripple carry adder. And if you want to do a 32-bit ripple carry adder, the carry needs to go all the way, right? But you can turn this into a carry look-ahead adder. With additional logic, you can basically pre-compute the outcome of the 32nd bit, for example, based on what could potentially happen in the earlier 31 bits. And now your adder becomes huge because in the end, you need to actually pre-compute all of those possible outcomes and then select the right one, depending on what carry actually got generated. That speeds up your adder a little bit more, sure, especially if you do it at a coarse granularity, not a single block granularity. You could actually apply similar techniques. You could do some look-ahead techniques to speculatively allocate ports and then verify whether you allocate, but those things actually complicate things even more, right? So these are actually interesting ideas that you can apply in a router design or any kind of sequential dependence. Whenever you have a sequential dependence, you can actually speculate and then verify, right? This is another example. But we didn't do that because we thought it would actually increase the area significantly. Actually, some other work did that. Some concurrent work, or a bit earlier work did that. And they showed basically a huge increase in the area of the router if you do this oldest first arbitration. Okay, so basically this is our router, a blessed router, bufferless router. Priority sort, port allocation. And it turns out if you implement an RTL, you get 43% longer critical path. Yes?
So if I understand this right, it's possible for only a single one to be granted. Like if on that on that example, the second one wasn't sent to north, but south instead, every other one would be deflected.
Exactly, yes, exactly. Yeah, so then the question becomes basically, there are other ways of actually designing this router, right? Because you don't know what's coming next. So you're lucky in this case that it was not sent to south, right? More deflections. Exactly. Yeah, exactly. That's a very good point, basically. Now we're going to add even more deflections and reduce the complexity even more. Okay. Yeah. So this turns out it's 43% longer critical path. Then the question is there a cheaper way to route while guaranteeing line-like freedom? And this paper's answer is yes. And then the question becomes, what is really necessary for line-like freedom? Anybody? Yes.
Potentially that there's an absolute order where it's impossible for something to come, like to be inserted at a earlier order. So that all new things that end up at the back somewhere.
Okay. But that's the total order, right? Okay. Okay, maybe you're going somewhere. Anybody else? Yes. I cannot hear, sir.
Over a flit for a limited number of times.
Oh, I see. Basically, you limit the number of deflections, for example. But then how do you decide? Like, let's say 5 flits are deflected 10 times. Which one do you prioritize? You need to have some sort of ordering, basically, to break the ties. Yes?
You need some sort of global information among all the flits.
What information?
Global information. Each router is also aware of all the other flits that are being deflected, ideally. Or maybe we can just attach some counter to each flit, and each is deflected, we do counter.
I see.
Since we prioritize this flit.
It's similar to your colleague's idea, but that doesn't work also. Because in the end, what happens is if you're really congested, all of the flits counters will be 0, or most of the flits counters will be 0. So you're back to square 1. I think he was onto something. I don't know if this is the same as what we have, but basically we have a total order. Total order is great. New traffic is lowest priority, like you said, and older traffic has higher guaranteed progress. But basically, this total order is completely unnecessary, right? If your goal is to really provide live lock freedom only, it's just enough to pick one flit, whatever flit it may be, randomly pick, and prioritize until it arrives to its destination. That's it. And then once it arrives, somebody else becomes the golden flit. And again, that could be random, right? Basically, you have a completely partial order. One flit is golden, everybody else is non-golden. There's no priority between everybody else, let's say. But this flit makes guaranteed progress. And as long as you pick another flit and it gets prioritized until it reaches this destination, eventually you drain the network and there's no live lock, right? That's the idea, basically. And this greatly simplifies. Basically, ensure any flit is eventually picked. Make sense? Yes.
Won't the other routers then, won't they need to know when a golden?
Exactly. Basically, this has to be done in the entire network. So prioritize until arrival in the entire network, not just one router. Sure.
But then once a flit has arrived, then once a flit stops being a golden flit, then every other router would now need to be informed that we don't have any more golden flits, so pick a golden flit.
Yeah, you will see. I mean, then now you're getting into the implementation, right? How do you implement this? There's an easy way of implementing this, actually. Yes.
I feel like this is a very loose definition then of live lock. I mean, it guarantees we always make progress on some flit, yes, but it doesn't guarantee that some flit doesn't stay in the network forever.
It guarantees that, because any flit is going to be golden at some point. So nobody's going to stay in the network forever with this algorithm. Yes.
But this only works if there's a limited number of flits, right? Because if you if there's always an additional flit, who guarantees that there isn't a flit like that's been there forever while all the new ones get the golden to be the golden flits?
I don't understand that, because in the end, basically what I'm proposing is just this, basically, right? You pick one flit, it becomes golden, and it gets prioritized until it arrives at its destination. It's out of the network. So that goldenness is you guarantee that gets prioritized. And then you pick another flit, it also goes out of the network. And then you pick another flit, it also goes out of the network. Another flit, it goes out of the network. So basically, I don't see why some flit would stay in the network forever.
But just suppose there is one flit that has been there for a very long time, and there's a constant flow of new flits. And by I don't know, by accident, you always pick the new flit. Then the one that has been there forever will stay there forever if you always pick the new flit.
Well, ensure any flit is eventually picked. That's number 2. Yeah, right? But this is live lock freedom. Your goal is to prevent live lock. Your goal is not to do high performance. Maybe you'll achieve high performance with other techniques, right? Yes, go ahead.
Okay, then I guess the question becomes, how do we pick any flit eventually?
There you go. So you agree that this is live lock free, right? So how do you pick it? Yes.
I also agree with what they said, because let's assume this cloud, the number of flits in the cloud never stays constant. We just keep adding more flits in it. And let's say
about on-chip network. Why would you overflow that cloud?
There's more requests constantly.
Yeah, but it's a throttling network, right? You have limited links. Okay, this is a bufferless network. We're talking about a bufferless network. But even in a buffered network, you have limited space, right? You cannot keep injecting stuff, right? That's the assumption.
So the assumption is that once everybody has a request pending, they all just wait to serve.
Not all the requests are served, but they cannot keep injecting into the network because that network has limited capacity, right?
So let's say we have like 5 processors and they've checked their requests into the network. We pick one of them. Now we have 4 pending requests, but the 5th processor has queued another request.
Yeah, it can inject it, yes.
So then there is a possibility that those 4 queued requests are now no longer going to be served because we're picking randomly. So
I didn't say it's randomly. It doesn't matter, actually. You just need to guarantee number 2. Ensure any flit is eventually picked. It's not random. It could be random, sure, but random is very hard to implement, I think, and coordinate across all of the routers. Right? Okay, any other arguments against this? Yes.
It's not on this, it's on the weaknesses of this mechanism. I think one of the weaknesses is that this deflection mechanism causes a 43% longer, the live lock freedom causes a 43% longer critical path than if you were to use a buffered router. And yet the performance under a low load injection is the same between bless and buffered routers. So how can that be?
Well, the question is that 43% affecting your frequency, for example, right? So we will see results with that 43% included later on. Those were not in the original paper.
Oh, so
yeah, original paper did not take into account that there is a significant effect on the router latency. So basically, original paper assumes that the router latency is the same between buffered and bufferless, right?
Okay, I think I'm a bit confused. I thought that because I'm talking right now about the critical path.
Yeah, critical path affects your frequency, right, in the end.
Is this critical path within the router?
Within the router, yes. So your router may be may not be clocked at a high bandwidth, sure, compared to a buffered router, and that is going to affect performance, sure. Yeah, but if your injection rates are low, again, maybe you don't need that much high performance routers also, right? When you're congested, absolutely, yes. You need high bandwidth and you want to clock your router very high speeds, but you will not be able to do that with bufferless.
Okay, maybe we can talk about this during the break or something.
Okay, sure. Okay, so everybody's okay with this algorithm now? Then the question becomes, how do you pick? So basically, which packet is golden, right? You select the golden packet so that a given packet stays golden long enough to ensure arrival. And this is maximum no contention latency at the very least, because you're prioritizing this packet. So you should give it at least maximum no contention latency plus some buffering, because the paper discussed that. And the selection rotates through all possible packet IDs. So again, we know how many packets can be present in the network. We have a global structure of the network, right? Every node can inject a limited number of packets into the network. And you can enumerate all packet IDs. Everybody has a packet ID. And then you have a static rotation schedule that every router obeys. At given time, packet ID, at this point in time, packet ID 30 is prioritized. Every router knows this. Right? And some packet has a packet ID 30 because it's associated with a buffer in a processor or in an agent that has injected that packet into the network. And every packet is a unique ID. Make sense? And then that packet is prioritized for long enough such that it gets into its destination. And then every router knows at this point, packet ID 31 is the highest priority or golden packet. That gets prioritized for long enough. And then every router again knows packet ID 32 is prioritized. So basically, it's a simple counter over packet IDs, and every router obeys that static schedule. That's what you can do with a known network structure. And we're exploiting the characteristic of an on-chip network, right? This network structure is not going to change. Even if it changes potentially, as long as you have you go through a maximum number of potential packet IDs, this works. Okay, so basically you have the packet header as source, destination, and request ID. That's the packet ID basically. And at cycle 0, golden packet is, this could be your packet ID. This is how you can form the packet ID, right? Source 0, request 0 is the golden one. Now the golden packet may not exist in the network because source 0 may not be using request 0's buffer, right? It did not inject anything. Well, you're wasting that golden, it's fine. At cycle 100, source 1's request 0 becomes golden. At cycle 200, source 2's request becomes golden. Yeah, you keep doing this basically. Yes, clearly the delay at which you get to a packet, there's a maximum delay that a packet becomes golden. And that delay is very large right now. It's the number of nodes times number of requests, right? But that delay is not what we're optimizing. We're optimizing the router right now. The question is, how often do you really need this live lag freedom, right? Yes.
You said that like if the gold isn't present at the time, then like something happens. What exactly happens? Like, does it skip to the next one in the static schedule?
No.
Or
I mean, this is
nothing?
Basically we're pushing the limits. We're saying what is the minimum thing that you really need for live lac freedom. You could certainly extend this saying, oh, there's a silver packet also, right? And then there's another level, bronze packet or something. And then you have 3 levels of priorities, right? But if it's not golden, then you don't get prioritized. Yeah, it's sent around based on the routing algorithm, right? It could be random, it could not be random, right? Yeah. You would still want to reduce deflections, I think. In this work, we didn't try to reduce deflections, but in the next work, we'll discuss how to reduce the deflections a bit more. Okay. Okay, so basically you only need to properly route the golden flit, right? If you look at this, there's no need for full sorting right now. And there's no need for sequential allocation. Basically, golden flit routing with 2 inputs is very simple. It's essentially a very simple permutation network. So let's route the golden flit in a 2-input router first. This is the algorithm that we're going to use basically. Pick a winning flit. Winning flit is the golden flit, otherwise random, as your colleague suggested. It doesn't have to be random, but random simplifies things, right? You don't need to enforce priorities again. And then you steer the winning flit to its desired output and deflect the other flit. So golden flit is always routed towards its destination, and there are no guarantees on any other flit, basically. And each of these 2-input routers actually make decisions independently. So deflection is that now you make a completely distributed decision in the router. So let's take a look at this. So golden one is golden, yellow, I guess. And the other ones are not golden, basically. So in this router over here, randomly, the red one wins because there's no golden flit. And you need to swap because the destination of the red one is here, as you can see, and the destination of the green one is here. So green one got lucky, let's say. Not yet, because there's another decision that needs to be made by this router, right? It didn't get lucky to go to its destination yet. Okay, here we have a golden flit, so yellow one wins. So there's no swapping because yellow one needs to go here. Okay. And then, yeah, we did this necessary swapping, etc. Now here, green one wins randomly. So it got lucky. If your random choice was for the, well, I guess in this case, it doesn't matter. In this case, it didn't get lucky. Green one got lucky here, yes. And here, well, I guess it got lucky here also because the blue one happened to be here, right? If another color was here, for example, if something was deflected over here, then green one would not have potentially gotten lucky. So basically, there's an amount of luck because of randomness, right? So, but that's how each of these 2-input blocks make a decision, right? And here, golden flit is again prioritized. So it gets to its destination, and the red one gets deflected. So here, 3 of the packets or flits go to their destinations, productive ports, and only 1 deflection happens. And you could argue, yes, maybe we got a little bit lucky with this one. Does that make sense? So now the router is actually this. This is basically our router. So instead of having priority sorting and port allocation, remember priority sorting was longer than this one to begin with. We basically have this permutation network that makes decisions in a distributed manner. And internally, you have crossbars, as you can see, right? So a network is really a network of networks in the end. Okay, so basically, this is what we have. Well, this is our permutation network-based pipeline. Oh, this is the permutation network. Now we're going to tackle the reassembly buffer problem because there's another problem over there, completely independent. So in the worst case, every node sends a packet to one receiver, right? Every node in the network is essentially you have a hotspot. That receiver is getting the packet. So the receiver needs ON space because there's N sending nodes, right? So this space could be quite large, basically, depending on how many nodes you have. So you can say, why can't we make reassembly buffers smaller? So if you make reassembly buffers smaller, you run into deadlock issues. Let's take a look at this. So this is your network. This is your receiver, one of the receivers. It has 2 entry reassembly buffers. And assume that the packets are, each packet has 2 flits. And you have many senders, as you can see. So somehow, the green flit, one of the green flits arrives. One of the blue flits arrives. Now you run out of reassembly buffers. Now injection happens in such a way that yellow one comes and reassembly buffer is full, so this yellow one cannot be ejected out of the network, right? And somehow the network gets filled with yellow and red ones, and these poor other flits don't get injected for whatever reason. It could happen. Now your network is full, right? Your network is full. It cannot accept any other requests. Your reassembly buffers are full. Nothing from your network can get ejected because everybody's targeting this node. You cannot inject new traffic, but to continue to solve the problem, you really need to be able to inject these two so that these reassembly buffers are completed and they can be deallocated, right? Basically, forward progress is blocked. This is a circular dependency now. Makes sense, right? So everybody in the network right now is waiting for these reassembly buffers. Okay, so clearly this is a problem, and this is, yeah, and this needs to be solved basically. If you have a buffered network, this problem doesn't exist actually, and you can think about that. So what if every sender asks permission from the receiver before it sends? That's one way of to avoid deadlock, right? So sender basically says, I want to reserve my slot, and the receiver says, yes, it's reserved, so send your flits. And now it sends its flits. So basically, this is reservation-based flow control. And if you do this, it adds additional delay to every request. Yes, it works. You can prove that it works, but there's too much delay for every request because you need to do one round trip to get permission and then another round trip to send the data. So this is pessimistic, right? This is really the really pessimistic approach. So you can be optimistic and sender optimistically sends, assume that the buffer is free. And if that's not true, the receiver drops the packet and sends a negative re-acknowledgement, and the sender retransmits. So you can see that again, the sender sends two flits. One of them gets dropped. You get a NAC. Now other packet completes. Then sender happens to retransmit during that time, and it gets the reassembly buffer. And then eventually it receives a NAC, and it frees the data. So basically, this requires retransmit buffers to be underutilized, if you will, because you need to get the ACK to free the data, because some of your packets may be dropped, right? That's very similar to buffering in a router, but now we're talking about buffers outside the routers. Because, okay, you can say buffering in a router, we can eliminate that, but now you're pushing the problem to the edges of the network, and that's absolutely true. The edges of the network are now having more buffers. But maybe some of those buffers already exist, and we're going to talk about that also. Yes, so in this case, no additional delay in the best case. That's good because you're dropping, but now you have a transmit buffering overhead for all packets. You need to wait for the acknowledgement. And also there's dropping, right? That happens. Potentially many retransmits happen because a lot of things are being dropped. So your network is probably not utilized very well. So this, again, a simple solution. There's no easy way out of this, I think. But basically a simple solution that tries to get the benefit of both worlds, reservation-based flow control as well as dropping-based flow control, which were the two approaches, is retransmitting only once. Basically, we transmit only when space becomes available. If you get dropped, ask for a reservation or automatically get granted a reservation. And the destination basically tells you when a buffer space is available, and then you retransmit. That's the idea of retransmit once. Receiver drops the packet if the buffer is full, and it notes which packet it drops. When space frees up in its buffer, receiver reserves space and tells the sender to retransmit. And yeah, okay. So let's take a look at this. At the first try, the sender sends. Receiver says, oh, I don't have buffers. Drop. And then it says, oh, I have something pending from node 0, request 0, which is this one. And I'm going to notify it when I have buffer space available. And when it has buffer space available, it reserves it and notifies sender to send, basically. That's the idea. So this is retransmit once. It doesn't have the overhead of reservation-based flow control, because reservation requires every request to be reserved buffer space. Here, you're optimistic the first time. And yes, you may not get the buffer, but if that's the case, you will be on the list of reservation, basically. And the receiver will reserve the buffer for you, and then you will retransmit at that time. So retransmits are limited to only once, and reservation is not on the critical path. Reservation happens only when necessary, meaning when the buffer space is not available. Yes?
Yeah.
You're sending at the same time now.
Are the NACs sent over the same network? So do they only need those?
Buffer space, basically. Yeah, I mean, yeah, that's a good question, basically. You could send them over the network, but they don't need the buffer space, yes, because it's just a signal, right? It's not the same kind of buffer. Usually this sort of buffer issues happen with data packets. It's good to, whereas NAC is a very simple control packet. Yeah, but I mean, in general, people specialize these networks. So NAC actually has a very simple control network where things are sent. Yes?
Could all the routers see this NAC coming and for instance,
potentially, yeah,
prioritize it next time they see like the
yeah, potentially, yeah. I mean, we didn't explore any of that, but potentially, yeah, you could make use of this information, right? Because NAC probably says, oh, okay, somebody is out of buffer space, so let me not send it over there. So you can actually imagine better flow control methods with more information like this. That's a very good idea, I think. But we didn't utilize any of that. So you can actually optimize a lot of these things in the network because you have a lot of information that you can collect over time, right? Yes.
So to make sure I'm understanding this, you're using store and forward here, right? For the bufferless routers in Bless because
wait. There's no store and forward, right? Basically, bufferless routers is just there are no buffers. You get a flit on the link. You send it to some other an output link.
Okay, so these input and output buffers are they're not per router. They're like
these are endpoint routers. Yes, sender and receiver.
Okay, and then I guess also then is there any difference in the requirements for these sender and receivers compared to if you used cut-through flow control with buffers? Because it seems like they also have the issue of having to having to repiece together packages, right? Since the flits are sent separately.
Yeah. Okay, so I think it's a different issue basically. Here. Yes, you need to store packets. Okay, I'm trying to understand. So these are not traditional router buffers, right? They're the endpoint buffers, which are collecting, either keeping the stuff that they're sending or collecting stuff that's coming to them, right? Yes, buffer efficiency is a problem over here also, no question about that. And you could imagine some other methods of keeping your buffers better utilized, right? You could, for example, have a global buffer and try to allocate from it such that your efficiency doesn't look like this in this particular case, right?
I guess just make sure, like the rest of my question is that I think one of the weaknesses stated is that Bless requires larger reconstruction buffers. Mm-hmm. And then I was wondering, and so like that is a weakness, or I guess larger is comparative, right? What is it comparing to? Oh. I was assuming it would be comparing to something that used buffers.
Wormhole, yeah, wormhole routing.
Oh, okay. Yeah. Because something that also uses buffers would be cut-through flow control. But I guess you would compare against the best within the category of the alternative.
Exactly. Yeah. Wormhole is the best basically because wormhole. Well, I think in the endpoints actually it doesn't matter as much, but in the endpoints, wormhole basically preserves the order of a packet. So you can actually play a lot of tricks that way, right? If you know the preserved order of a packet and you're going to receive the packet in order, you don't need to reassemble anything, right? Make sense? Yeah, okay. Yes.
So in this design, do the flits contain like all the routing information?
Yes. I mean, yeah, that's one of the downsides actually, because wormhole requires only the head flit to have the routing information, whereas bufferless routing requires every flit to have the routing information.
Routing information is an entire list of all the turns the packages have to take, or
no, it's just destination basically.
Individual routers then decide whether north, east, or west is
exactly. Every router basically does the packet switching. Yeah. Okay. So you can say that reassembly buffers actually already exist, and if you're doing cache traffic, especially, usually what you're receiving is really data packets from some other cache or main memory. Those are the big ones, right? Control packets are actually small. You can send at one shot. It's one flit packets usually, whereas data packets could be 10 flits, 8 flits, 16 flits, depending on, for example, if you imagine a 64-byte cache line and 64-bit links, you have 8 flits, right? And usually this issue arises when you have cache-to-cache transfers or memory-to-cache transfers. And we already have a structure actually that keeps track of this in machines. These are called MSHRs, missed status handling registers, or miss buffers. So whenever a cache requests some data, it already has allocated a miss buffer in the cache. That's the realization, basically. You have a list of outstanding cache misses with buffers allocated for each of those cache misses that you're waiting for. Let's take a look at that. So miss status is called a miss static handling register. It has some status, it has some address, and it has some data. Essentially, data could be flits that you're waiting for. And that's the idea. So reassembly buffering actually can be free. If you tightly integrate your core or cache or last level cache or whatever cache you're communicating with the network, then you basically get the data or get the flits into your data buffer in your miss static handling register. And you don't need to have another buffer in your system. This kind of breaks, let's say, or reduces the modularity assumption a little bit, right? Remember, we were talking, you have the processor, cache, network interface controller, router. And normally cache and router are decoupled from each other, right? Router has its own buffers, cache has its own buffers, but why? You're designing on chip network, why not couple them? That way you reduce the buffering requirements because you already have these buffers inside your system, right? That's the idea over here. Basically, this is what we believed actually when we started looking into bufferless, and this paper actually showed that you can do it. It requires tighter integration between the router and the cache, but that way you can get rid of the buffers because these buffers already exist. That's the idea over here. So basically you replace the reassembly buffers with miss buffers, MSHRs, which already exist. That also reduces the cost of the router now. So basically now you have a truly bufferless networks. Because endpoint buffers are also gone. Gone in the sense that you're reusing some buffers that already exist, right? So the argument that the endpoint buffering increases doesn't hold anymore because it's already there. Okay, so basically this is where we are, right? This is called cheap interconnect partially permuting router or chipper. You have a baseline bufferless deflection router, which looks like this. You have a long critical path sorting by age, allocating ports sequentially. We solve that by having a golden packet and permutation network. And then you have large buffers for the worst case for reassembly. And we solve that using the retransmit once protocol and using the cache miss buffers as your network buffers also. And your router now looks like this, basically. A little bit cleaner. Let's evaluate this. I think people are interested in evaluation. So we did a lot of evaluation with multi-program, multi-thread workloads, and you can read the paper for more details. And we use perfect L2 again to stress the interconnect. Because if you actually don't use perfect L2, the results are even better, let's say, because your network is even less utilized. So I think that's the overall conclusion. Other works actually showed that later after we showed our results. There was actually a lot of work on reducing the complexity of the router in different ways. Bufferless is one way, but there are other ways also. For example, you can make a mesh look like rings and limit the turns that you can take at different parts of the rings. That's one way of actually reducing the network. Because if you think about a mesh, it's like a ring, right? Or torus, let's say. It's like a ring on the X dimension as well as Y dimension. And if you can limit the turns you can take, then you can actually limit the router complexity. Your routers are not 5 by 5 anymore. Your routers are mostly 2 by 2. And only some routers have turning points, right? So that way you can actually get the benefits of a mesh with much smaller routers with some performance degradation. So this is some other work that came after we looked at this, for example. But a lot of those works basically show that your network utilization is usually not very high on the on-chip network. Unless, of course, there are some workloads that will stress it. But if you have perfect L2, you actually stress the interconnect a lot more. Okay, so we do some modeling, etc. You can read the paper. So let's take a look at the results basically. This is the performance degradation. And overall, performance reduces by about 14% compared to BLES, compared to buffered networks. So it's worse than BLES, but BLES is actually not as implementable, let's say. And mainly the performance degradation actually comes from these deflections that we didn't really control. So we're going to solve that a little bit later. And multi-thread workloads turn out to be even less. But there are some workloads that do not stress the network that much. Over there, the results look good. But there are some workloads that stress the network very heavily. Over there, the results don't look good. So as expected, kind of. But it's more practical. And actually, if you include the memory accesses, these results go down significantly because memory becomes a bottleneck right now. But I mean, you could argue that, yes, there are some cache resistant workloads. And in cache resident workloads, this is where network is not going to do well, right? So if you have a lot of traffic on the network, and that's true, no question about that. Okay, so power reduction on the other end is very significant on all workloads. You can see that it's 55% overall, in multi-thread even more, because multi-thread network is even less utilized in this particular case. And router area now reduces significantly compared to buffered. And critical path also reduces significantly compared to BLES. And it's very similar to buffered routers now. And buffered routers are optimized for decades, let's say. maybe this router can be optimized even more. I don't know how, but because anything you do, I think will increase the critical path slightly. Okay. Okay, I think we've covered all of this. Basically, yeah, I already said all of this, so I don't want to repeat it right now. Any questions? Yes.
How can the critical path of BLES be longer than that of a buffered router? And yet, I think you said earlier that the latency of the router actually decreases when you use BLES compared to.
Yeah, so I think the difference here is, say it again. How can this one?
Yes, yes. You said the critical path of this one is longer. Well, yeah, on here you see that it's longer than for the buffered router.
Longer than buffered, yes, because of the additional complexity of the oldest first prioritization.
Right, right, and then
sorting.
And then also, I guess this is like maybe like 20 minutes ago. You said that the results where BLES achieved like the same performance as buffered didn't even take into account the fact that BLES had lower latency.
Yeah. So we were very, very aggressive. Basically, we thought actually you could design a router that could be much faster if you eliminated buffering. But I will argue that we were not right.
So your thought was that despite the longer critical path with BLES, you could still design a router that had lower latency than if it had a buffer.
Lower overall latency potentially, yes, because with buffered you have much more pipeline stages, right? You need to do a lot more tasks, and usually the pipeline stages are I don't know, 3 cycles, for example. Maybe your clock cycle is a little bit higher with BLES, but you can get done with 2 cycles or 1 cycle potentially. Well, critical path is really a measure of how long your clock cycle is, right? But yes, it's not a measure of overall time that you need to spend to process a packet in the router. Absolutely. Because you may need multiple clock cycles. But of course, I mean, there's more detail over here because there are a lot of optimizations that were proposed for buffered also, some of which we applied, some of which we didn't apply. So I think the jury is still out, but I think the key conclusion is that now you're competitive in terms of critical path with buffered. And you don't need all the buffer management tasks that you need to do in the buffered. Yes.
So in this version of Chipper that was used for these tests, what was the cycle length of the static sort of scheduler for the golden filter? And was there anything being done?
I don't know. It's in the paper. Yeah, I don't remember. Basically, how often you basically cycle through the static rotation schedule, right? Yeah, I don't remember. But basically, it was determined. It's determined based on. So it's a function of your topology, routing algorithm, and flow control, right? You need to determine it on a per network basis. How big your network is. Basically, you need to for a given network, you need to know. If I prioritize the packet, how long will it take to get to its destination? And that should be at least that should be the value. Number of cycles with which you should prioritize the golden flit. Yeah, I think actually we have a technical report. I will show you extended technical report that goes into that worst case analysis in a little bit more detail. We couldn't fit that into the paper, but you can do a worst case analysis saying, okay, this is the maximum delay that you can get because of this. Live lock freedom mechanism. Okay. Yeah, maybe I will show that and then we'll take it. Yeah, this is the technical report basically. You can take a look. Okay, maybe we should take a break. How about coming back at 15:18? And then we will hopefully finish whatever we have. Looks like it's not snowing anymore. It is raining? Yeah, that's not necessarily good. Oh, there's something in chat. Oh, okay. Nothing. People on chat are not very, yeah.
That's a good question.
Yeah, sure.
Yeah, but I guess this is just zooming out to the philosophy again. I think the reason why we have routers was to separate computation from network management.
That's true, yes. Yes, now we're putting them together, right, closer.
And it's HR, right?
Yeah.
Isn't that HR that combines it? So like, I guess philosophically, why is that justified?
Well, I mean, philosophically, okay, there are two different competing philosophies here, right? One is if you separate them, they're clean interfaces. Yes, your design is more modular, sure, absolutely. And that's true, right? Whereas the other philosophy is you're in an on-chip, you're in an environment where you can minimize the resources that you dedicate to the entire system, right? Right. So from the perspective of that philosophy, I think this is justified. Yeah. But it comes at the cost of modularity and clean interfaces, sure, yes.
Okay. Yeah, I guess that's getting all in the context on chip.
Yeah, exactly. I mean, if off chip, then this is harder to do, of course. I mean, you can do it, but yeah, I think two competing philosophies clash here, and I don't know if there's a way to really merge them. Yeah. Because it's in the end, it's buffers, right? If you want to minimize the use of buffers, in the end, you can think of all of your data storage as buffers, and there's a central place where you have buffers and allocate them, but that's completely against modularity, right?
Yeah. I guess it's a question of how much can you violate modularity while keeping your design tractable. For the on-chip case.
I think, yeah. I mean, I think in the on-chip case, you can actually do this, right? It's because it's not that much. So basically, you need to somehow design this buffering integrated with your router, and it's not the router's core buffering, right? It's really an endpoint buffer. Yeah. So you could argue that this should have been in the endpoint to begin with. Basically, you can actually try to distract basically try to change the boundary of modularity, right? You can basically have an interface between the router and the buffer, and then still try to make things modular, right? Yeah.
Okay, I think I am sold on this.
Makes sense. Okay, good. Yeah.
I have actually like an idea, and maybe I can suggest it, and you can.
Okay, sure. Yeah. Let me turn off the mic. So now we're going to continue. I think there are a lot of good ideas also to make the bufferless router better. And I would encourage you to keep generating ideas and maybe even writing papers and doing evaluations on this topic, because I think it's extremely important, actually, especially going into the future. Okay, let me now introduce a little bit more on this direction, and then we're going to switch gears. So basically, I think it's good to push an idea that's really extreme, let's say, which is getting rid of buffers, all buffers, right? But it's also good to realize that at some point, that's not necessarily a good thing. And that's what we realized, basically. We say that, okay, you can actually keep optimizing this bufferless network. That's great, but it's going to be very hard to reach the performance of a buffered network at high loads. So can we do something different? And this is the next idea, basically. And the next idea introduces some buffering into the router, but in a different way. We're not going to use the buffering. Basically, not everything needs to go to the... So basically, when you do buffering in a traditional buffered router, everything has to go through the buffer. Maybe that should not be the common case. Maybe buffering should be used only in the uncommon case where you have deflections, right? That's the idea over here. And there are other ideas over here that I will quickly go through. So clearly, high deflection rate or performance at high load. You could try to reduce deflection rates if you're completely bufferless by doing better prioritization. That complicates the router a little bit. Yes. So the idea of minimally buffered deflection router is to have a side buffer to hold only flits that would have been deflected, right? Or that are deflected, basically. They're not going to be deflected. Basically, you're going to loop them back into the router with this buffer. You can also think of this as a loop back buffer, let's say. And then there are a couple of other interesting things that this paper does to reduce the congestion in the network and also reduce the deflections. And we will discuss that quickly. And basically, it still preserves the power and area compared to buffered routers. And it improves performance significantly compared to bufferless routers. Basically closes half of the performance gap with simple modifications. And it basically has the best energy efficiency of all the evaluated designs across many workloads while having competitive performance. And this is the paper, so let's go through it quickly. So we already talked about bufferless routing, that's good. Basically, our goal is now to improve high load performance, which is the hard part, right? By reducing the deflection rate or by reducing something, right? It's not just the deflection rate, actually. That's not. So there are multiple ways of improving high load performance. So what happens at high load, right? You get congestion in the network and things start deflecting a lot. You can alleviate that congestion somehow by throttling injection into the network, right? And that is something that we're going to briefly talk about. We've looked at source throttling a lot, actually, so that you basically throttle before the network gets congested. And that actually helps the high load performance also, because if you're too congested, latencies shoot up, and you're at that point of saturation throughput that you really don't want to be operating at. If you throttle early enough, then you basically reduce the latencies, and that's good for the bufferless network because things don't get deflected a lot. So throttling is a good idea, which we will briefly discuss, which we have discussed actually when we talked about quality of service and interference. But that source throttling is actually good. Beyond that, you can also do other things like add some buffering, right, as we will see. Okay, so let's take a look at, we've already discussed this. That's good. So basically, if you look at Chipper, it basically improves the performance of the router, but it doesn't do much at high load, right? It basically solves some practical issues. The question is, how do you avoid the performance degradation at high load? That's what MinBD solves. So what are the performance issues? Let's take a look at them quickly. So link contention, no buffers to hold traffic. Basically, whenever you contend it, you basically throw stuff at the links. And whenever you have a link contention, you cause a deflection. So can we actually prevent that? And that deflection may be good, right? Maybe it may allow you to actually go to your path by taking a scenic route, but it may also increase the congestion significantly. And then there's an ejection bottleneck. Because your links are oversubscribed, you have no buffers. It turns out this actually leads to an ejection bottleneck, meaning only one flit can be ejected per router per cycle. And if you have two flits simultaneously arriving at a destination, and this happens actually more often than you think when you don't have buffers, and that simultaneous arrival causes deflection. So you reached your destination, two packets have reached their destination, but the router cannot consume two packets. The destination cannot consume two packets, cannot eject two packets. It deflects one and takes one. So you basically remove one packet from the network, that's great, but you basically cause more congestion by not removing the other one. So the other one now takes the scenic route, turns around. This is like when you get to for some reason your plane cannot land at an airport, right? What do? One plane lands, the other plane deflects, and it turns around and it takes 10 more minutes, and it causes congestion over there. If you actually have this ejection bottleneck at the airport, then you cause congestion around the airport, right? It's very similar to that problem. And then there's a deflection arbitration problem, which is there's unnecessary deflections, as some of you realized, right? Because of the random choices that we make. Can we actually reduce those unnecessary choices, unnecessary deflections? And we're going to solve the problems by using side buffers, basically increasing the ejection bandwidth, and basically introducing a little bit more complication in the priority scheme, local. So golden flit, if you remember, is global because it serves the purpose of live lock freedom. But you can locally pick a packet flits and ensure that it wins its arbitration, right? At least one packet will not be deflected in that case. That's the idea. Now, of course, you could extend this locally to more, but now you're adding more priorities. Okay, so hopefully I'll give you the basic ideas, but let's take a look at this. So buffering a flit can avoid deflection when there's contention on the link. But input buffers, as it is done today in buffered routers, is very expensive. All flits are buffered on every hop, and large buffers are necessary. So basically, buffering is the common case today, right? Can we actually make buffering the non-common case? That's the idea. And the idea is very simple. Add a small buffer to a bufferless deflection router to buffer only flits that would have been deflected. Would have been is actually maybe not the right word because you're still deflecting the flit, but you're not deflecting it to another router. You're deflecting into the side buffer so that it's going to get injected. So this is our baseline router. This is a chipper router that you remember. And now we've added the ejection and injection link. So basically, when a flit comes, you first check for ejection and it gets ejected. And you can also insert injection. This is one way of building the injection and ejection circuitry for the local node, right? And it's a good idea to eject first and then inject next because that frees up the link, right? If you do it the other way around, that's kind of not smart. Okay. So basically, these are destinations for the red packet and the blue packet. And this gets deflected. This goes to its destination. And the deflected one basically goes around, and at some point, it basically increases its distance to destination, right? So this is what we introduced. We have a small side buffer, and it's an injection buffer, basically. It's not a buffer on any of the input ports. So we're going to keep these free of buffers. But only deflected packets get allocated entries over here. So the red one goes here, blue one gets its destination, blue one goes on the link. Red one, instead of getting deflected, we can remove up to one deflected flit per cycle from the outputs and place them into the side buffer. Makes sense, right? Now the side buffer is part of your injection circuitry. You could actually put it into your injection buffer also, but yeah. That depends on where that injection buffer is, I guess. If it's in your cache, for example, like we discussed, now it may not be a good idea to actually inject it into your cache at this point, right? So this is where some of that decoupling of the router and the cache may help. Okay, so this goes into the side buffer basically. And it tries its chance whenever a pipeline slot is available in the router. And then hopefully it gets a slot in the next cycle if that particular injection link is not contended, and then it gets to its destination. So you can see that this reduces the latency potentially, right? By giving a second chance to these deflected packets, or maybe a third chance. It depends on how long they stay in this buffer, of course, right? But you don't immediately deflect in a sense. And this buffer size, even a buffer size of 1 is good. 4 is actually quite good also, as you will see in the results. Of course, as you keep increasing it, then you have more complexity. Does that make sense? Yeah. But the key idea is basically it's not the common case. Okay. So I think we've discussed this. You buffer some flits and deflect other flits at a per flit level. Deflection rate reduces relative to bufferless routers. So a 4-flit buffer, for example, reduces deflection rate by almost 40%. And relative to buffered routers, if you think of this as a buffer, again, it's a buffer. It's not managed in the same way. It's actually completely locally managed, right? There's no credit, etc. There's no buffer management, except for the local management that you do. It's more efficiently used also. There's no need to buffer all flits. So you can basically get similar performance with very small amount of the buffer space. Okay, let's take a look at the ejection bottleneck. Basically here, flits deflect unnecessarily because only one flit can be ejected per router per cycle. And it's interesting, this is the real numbers. In 20% of all ejection cases, whenever you're ejecting one flit, more than or greater than equal to 2 flits could have ejected if you had the bandwidth. So basically, there are a lot of simultaneous arrivals to a destination router. And all but one flit must deflect and try again. Now, what does that mean to try again? You basically get deflected and turn around and eventually get back to this router. And these deflected flits cause additional contention. Right? Of course, if you have a side buffer, you can actually use that also here. So these ideas are actually partly complementary, partly eating each other benefits. But if you have an ejection width of 2 flits per cycle, that also reduces deflection rate by 20%. So that sounds good, right? And that's the idea, basically. Allow 2 flits to eject per cycle. This, again, complicates the router a little bit, sure. But it's not that bad, right? We're not playing with the core of the router as much. Where instead of ejecting 1, we're increasing the bandwidth. So this is the baseline. This poor red packet, even though it needs to be ejected, it came to its destination, it now gets deflected. If you have a side buffer, it goes here, potentially. But again, now you need to provide the path to go to the ejection part. So side buffer and employing this idea, dual ejection with side buffer actually complicates the router a little bit more also. But now the red packet comes back and gets ejected. Well, it would have been nicer if you actually had this 2-wide ejection bandwidth, right? Makes sense, hopefully. And these are relatively simple changes to the router. Again, all of these are local changes. No changes. None of these changes need to be communicated to any other router. I think that makes a difference, actually, in terms of the design as well. Okay, of course, now the question is, right, you run into fair comparison issues. What if the baseline had dual ejection? So it turns out baseline doesn't benefit from dual ejection that much, because this is a big problem in bufferless, because baseline is buffered, right? And in buffered routers, this is not that big of a problem because you're going to buffer. The request is waiting in your buffer to be ejected, basically, right? So it's not that big of a problem. Whereas in bufferless routers, you keep circling around, you cause congestion. And basically in the evaluation, and this is always good to do in evaluations, you provide the performance of dual with ejection while not charging for it in terms of power and area. So magically in the baseline, you have dual ejection compared to, but you don't get the power and area overheads, which is not a lot, granted, but still. Okay, and the last thing is actually another simple idea. So these are simple ideas that have actually a lot of impact on the router efficiency. And this simple idea is basically the problem is we saw that deflections can occur unnecessarily because we use simple priority schemes, right? Random arbitration, for example. Age-based priorities are not good because they lead to slow arbiters. And we discussed the state-of-the-art deflection arbitration. You have golden packet and a two-stage permutation network. And well, this is good for ensuring forward progress, but this random arbitration that leads to fast critical path actually makes increases the deflection rate compared to age-based priorities, for example. Okay, so let's take a look at this. I mean, we've seen this already, right? You pick a winning flit, otherwise, if there's a golden packet, then that's your flit, winning flit. Otherwise, you randomly pick something, and that is the winning flit. And then the winning flit gets this desired output if it's available. Right? So highest priority flit always routes this destination in this case. And otherwise, things are randomly chosen locally. And we've seen this already, right? Basically, you have unnecessary deflections in these fast arbiters, right? I kind of mentioned this when we actually looked at it, but let's take a look at a real case. You have these flits. All flits have equal priority. There's no flit golden here. Ignore this yellow one. Assume that it's not golden. So arbitration is completely pseudo-random. So red flit wins the stage. So it gets routed towards its destination. Blue flit gets misrouted, let's say. Well, I guess we don't know its destination, so I'm not going to call it misrouted. Green flit loses at the first stage. So it gets misrouted. And the yellow flit, which is not golden, goes that way. So in the second stage, now the red flit needs to get lucky to go to its destination, right? If you're doing pseudo-random arbitration. But if it loses, you have a completely unnecessary deflection you could have prevented. So randomness actually is not good, as you can see in the decisions. So basically, add another priority level, a local priority level, and prioritize that flit to ensure that at least one flit is not deflected in each cycle. Now, basically, highest priority is the golden packet in the network. This ensures correctness. Next highest priority is locally, one flit per router per cycle. Again, chosen pseudo-randomly, and it's local to one router to enhance performance. So let's take a look at the example that we showed earlier. So all flits have equal priority. Nothing is golden here. But red flit becomes silver, meaning locally this router decides, oh, I want to pick this red flit, and it's the highest priority. And it has minimal logic to actually prioritize that. Red flit wins at the first stage. And then green flit is deflected. And then red flit, now you ensure that because you prioritize red flit wins at the second stage also. So at least one flit is not deflected in this particular case. That's the idea. Yes, it does complicate the router a little bit, but it's not nowhere near full ranking across the flits. Of course, you can say now bronze flit, etc., and then you're complicating the router even more, right? Okay, so that's basically the minimal buffer deflection route. So the link contention problem is reduced with a side buffer. Ejection bottleneck is reduced with dual with ejection. And unnecessary deflections are reduced by a two-level priority scheme now, one for correctness and the second level for performance. And the key thing is everything that's added is local to every router. No other router needs to know any of these decisions that are made. So we're still keeping a lot of the benefits of bufferless routing, right? You can say, oh, yes, you're adding buffers, but it's not the same kind of buffers, right? It's not the same buffering. So, but we cannot call it bufferless anymore, right? Because we did add buffers. That's why this is minimally buffered. Okay, so we discussed this. Let's take a look at results quickly. Again, you can read the paper for more detail. And there's a lot of analysis in this paper. So actually, there was another paper that was published around that area time frame from some folks at Purdue. Basically, these folks proposed something more complicated. The idea is you have a hybrid network. One is bufferless and the other is buffered. And then you basically do coarse grain switching in the mode. So if you have high load, you switch to the buffered network. If you have low load, you use the bufferless network. So, I mean, it's an interesting idea, cool. Yes, it's a hybrid network, but now you pay the cost of two networks. And then, yes, they show basically energy benefits. So you can actually reduce the energy at low load significantly while not losing performance at high load. But this is actually quite high overhead in terms of design. So you still have to design a buffered network with all its downsides, plus a bufferless network. They basically use bless in their network for the bufferless network with all its downsides, right? Okay. Okay, I'll go through this quickly. Yeah. Yeah, okay. So this is basically overall performance results. You can look at the different mechanisms, side buffer, dual ejection, and silver flits, and then you can combine them. There's more combinations in the paper. But you can see the deflection rates reducing, right? Baseline, it says 28%. Some workloads, okay? These are the workloads that lead to 28%. And if you actually use a side buffer, it reduces the deflection rate, as you can see, significantly. Dual ejection also reduces the deflection rate, and silver flit, they all individually reduce the deflection rate. I think, yeah. Yeah. So side buffer alone is not sufficient for performance because there's an ejection bottleneck that remains. So if you actually add these three things together, let's take a look at the last one over here. All of the ideas added together, your deflection rate reduces significantly to 10%. And your performance improves significantly. We'll see performance more, I think, in some of the other slides. But you can see that you can reduce the deflection rate if you play these tricks. Okay. So that's the overall performance improvement you can see. But this is, I think, more interesting, perhaps, to look at in terms of performance. So overall, you get better performance over chipper, especially at high loads. Now, your high load performance improvement is significant. But still, compared to buffered, your high load performance is lower. But it's not bad also, right? So if you actually say equal buffer, equal amount of buffers, you're better than that equal amount of buffers over here, even at high load. So this is a measure of load. You can see the injection rate over here. But these are real workloads still. We just we just divide the real workloads in terms of the injection rates that they have into the network. So basically, overall, compared to chipper, you improve performance, especially at high loads. So you can see that low loads, it doesn't matter. In fact, in low loads, sometimes, I don't think you lose performance. You do lose performance sometimes because you have some additional overhead in your router, right? But at high loads, your performance improvement is significant. Okay, and at high loads, now you get much closer to the buffered, as you can see, right? But still, there's a gap. You can say, okay, maybe I don't care about that gap, but there are workloads that will put you in that gap, let's say. But the interesting thing is, if you have a buffered router, I think this is called, this is 4 virtual channels and one buffer per virtual channel. You get similar performance at much lower the buffering space. So if you really want to get higher performance, you need to increase the buffering, clearly. Okay, there's a lot more results. I'm not going to go through this in detail, but you can see a lot of analysis. But I think this is the state of the art in minimal buffered networks or bufferless networks, let's say, bufferless in parentheses or quotations, sorry. But you can see the power results are still quite good, right? In fact, power results are better. Okay, I don't know why this is not doing. I mean, these are results that we see. But basically, you can see that dynamic power increased with deflection routing. Chipper actually increased the dynamic power. Static power reduces a lot. And dynamic power reduces in minimally buffered networks, as you can see, compared to chipper. That's good. But there's some small amount of increase in the static power because we have these side buffers now, right? Okay. And this is interesting also. Basically, here we are looking at power versus weighted speed up. You can think of power performance spectrum. The paper has a lot more detail. But MinBD is actually at a quite good point over here. This is the adaptive flow control. Basically, the system that can switch between bufferless and buffered at different loads. But you have to implement both. You can see that its power is actually quite large still. But yes, its performance is still higher than MinBD. So from a performance perspective, MinBD is actually at a much better space compared to any prior bufferless network. And it's the most energy efficient. Yeah, let's take a look at die area and critical path. So clearly die area will increase because we're adding some more overhead to our router. It's only 3% compared to chipper. So there's still a significant benefit over prior buffered systems. And then critical path also increases a little bit. Yeah, that's unfortunate, but again, that may not be that bad, right? 8%, it depends on how much you're going to clock, and who knows, maybe there are other techniques that would reduce that critical path. So buffered routers are actually quite competitive in terms of critical path. Okay. Okay, I've already said all of these, I think, but this is really the state of the art in terms of at least mesh topologies, right? We talked about hierarchical rings, and with hierarchical rings that you could do actually a lot of interesting things. But here we're optimizing a 4x4 router, let's say. Once you go to hierarchical rings, your routers become simpler also, and those are 2x2, and you actually have a lot less complexity in your routers. Okay, any questions? Maybe people have other ideas. So at high lows, deflection rates are still a problem, actually. Some of the ideas that some of you have discussed are still applicable. Okay, so let me briefly talk about throttling. We talked about throttling in an earlier lecture, but we actually looked a lot into throttling also, and this is a good idea again. Ideally, you would like to employ all of these techniques together. So at high loads, you have a congestion problem. And this is true actually in buffered networks also. So throttling is a problem in any network, right? If you remember this picture, let's draw that picture again. Yeah, I gotta stop sharing, I guess. I gotta figure out what to do. That, advanced. Okay. Yeah, I think throttling is a general idea for enabling congestion control in all networks. Let's do this. So remember this curve over here. That's the load latency curve. So this is buffered. Maybe this is bufferless, right? And if you're operating at this point, it's not good, basically. You're congested and there's a lot of deflection. If you actually pull your operation point to somewhere around here, you're less congested and your deflection rate reduces significantly. So the idea of source throttling is to try to operate at a point that's reasonable, not unreasonable. So at some point, this becomes unreasonable and your deflection rate also shoots up, right? And that's true for a buffered network also. It's not a deflection rate in this particular case, but your latencies shoot up, right? At some point, your buffer rate is unreasonable. A buffered network is unreasonable to operate. You don't want to be operating around here, but maybe by throttling your sources so that you can reduce the utilization of the network, you can reduce your latencies. So source throttling is a general idea that essentially brings the network from unreasonable operation points to more reasonable operation points. Unreasonable operation points may lead to a lot of congestion. And this is true for any network, basically, any network. Internet has this property also. In fact, in our SIGCOMM paper, we look at the differences between internet type networks versus on-chip networks. Okay, let's switch camera. So throttling is a way of controlling the load, essentially, on the system. So it has really nothing to do with bufferless versus buffered. But of course, bufferless networks are much more vulnerable to load because they don't have buffers, right? Okay, but basically, there are interesting observations here. That if you have a lot of applications injected into the network, there's sensitivity. Some applications are more latency sensitive, and some applications are more bandwidth sensitive. And how do you do the throttling becomes interesting, right? If you equally throttle all applications, all nodes, that's really not good for system performance, it turns out, because you were delaying some latency sensitive applications significantly. And the idea in this work is heterogeneous adaptive throttling. So it does application-aware source throttling, and it also changes the throttling rate on a per application basis as well as the network load basis. Again, I'm not going to tell you how you do it. It really depends on the design in the end, but your throttling needs to be heterogeneous and network aware. And it basically turns out it improves performance and energy efficiency significantly over other state-of-the-art application agnostic source throttling policies. So this is another example of where application or workload or system awareness matters. if you look at the previous source throttling policies that are described in the paper, they're just looking at the network. Oh, if my network injection rate, if my network is congested based on some metrics, let's throttle everything by some amount so that I'm not congested anymore. That's the network's perspective, right? But it's really about the system in the end, right? If you think about the system, who you throttle and how much you throttle matters a lot, because your goal is to improve application performance and system performance. I think this mindset of network-centric thinking versus more system-centric thinking is important, and that has happened a lot with a lot of these papers. I think a lot of papers actually in networks or on-chip networks at least became much more workload aware over time. Whereas if you look at the early literature, it's all about, oh, how do we manage the network better? Okay, so if you're interested, you can take a look at the paper. And we've also discussed bufferless hierarchical rings. I don't have time to talk about, but these are actually really interesting. So if you design a hierarchical ring, rings are actually interesting because rings can be mostly bufferless to begin with, right? It's easier to implement bufferless routing inside a ring because you have 2x2 routers, and 2x2 routers, you can actually make things a lot easier to be bufferless. But when you have hierarchical rings, that becomes even more interesting because now you can actually deflect into some other rings, right? For example, when you're trying to transfer from one ring, local ring, to a global ring, okay, if the global ring is congested, take another trip in your local ring and then come back. And of course, the structure of the rings right now matters, right? Maybe you have multiple local rings. If you miss one hop to jump into a local ring, maybe you jump into some other global ring. So actually, deflection works nicely with these hierarchical rings as well. And these papers actually talk about that. I think it's actually, and they also show that these hierarchical rings that can be very, very energy efficient compared to meshes, for example. Meshes basically over provision the link or the connectivity you have. Building a hierarchical ring actually can get you to a better space in terms of performance. But again, we don't have time to cover this, but I'd recommend you take a look at some of these papers. And this is the latest one that we actually finished last month. Yes. Okay, yes. Huh? A lot more what? Traffic. Well, Xeon Phi is what is Xeon Phi? Is this the Knight's Landing type of processor from Intel? Yeah. Well, I don't know what the design of their interconnect looks like, frankly. But I know they have many processors, right? But I don't know. Yeah. In the end, yeah, I cannot vouch for the design of their interconnect for sure. I need to know more about the design.
No, because I'm just curious that people really prefer ring. I see them all the time, even in, let's say, network designs, computer network designs for large-scale organizations. But it just seems not very.
Yeah, I mean, certainly the rings are limited, right? If you have a single ring, even if it's bidirectional, your scalability is limited. So I don't know how Xeon Phi used it with hundreds of cores, let's say. Yeah, it depends on the applications also, though. Yes, you may be high throughput, but if what you're targeting is completely compute intensive, you're not having a lot of communication, then maybe it fits, right? Or maybe it's a bad design choice. I don't know. But again, hierarchical rings, with a single ring, I agree. But if you have hierarchy of rings, you can actually make that even more efficient and higher performance than a mesh. That's what these papers show, basically.
Sure, thanks.
Yeah. Okay. Okay, there are more readings like congestion and congestion control in off-chip and on-chip and internet-like networks, and I would recommend these. Okay, I can talk more about this, but we don't have time. Maybe very quickly, I will talk about the study that we did with compared to the networking. When you compare the design of on-chip networks to the internet, for example, both of them suffer from some sort of congestion, right? On the internet, there's congestion, and there are congestion control mechanisms that people do, similar to source throttling mechanisms. Routers basically drop packets, and you detect that your packets are dropped, you throttle yourself, or sometimes acknowledgements can be sent as well. Basically, there are congestion control mechanisms, and people showed that on the internet, what happens is you can go into a mechanism, a phenomenon called congestion collapse. What is congestion collapse? Congestion collapse is basically your network basically becomes flooded, and essentially there's extremely little progress. People have used that to do denial of service attacks. So denial of service attacks on the internet cause congestion collapse, for example, on some particular parts of the network. So on-chip networks are similar, except they don't suffer as badly in the sense that because they're self-throttling, basically. That's one of the findings in the paper. Because the cores are self-throttling, the congestion collapse situation is not as bad as it is on the internet, because internet is any node can keep on injecting packets, right? In fact, you can write traffic that just injects packets on the internet. You don't need to wait for the packets to come back. Whereas that's not the case in on-chip networks. I mean, you could think about potentially writing a malicious application doing that, but at some point the cores are throttling, right? You don't have access to hardware that keeps always injecting networks into the node, which is not the case on the internet. Okay, so basically this work also looks at an application-aware congestion control mechanism, which you can read about if you're interested, which is scalable. So as I said, you could do heterogeneous networks. So especially if you want to get performance and power at the same time. This work talks about heterogeneous networks. We don't have time to talk about it. Very interesting. And existing networks are already heterogeneous, like the Tylera networks, but they're statically scheduled in the sense that different types of traffic go to different networks. Our goal here was to actually make things dynamically scheduled to balance the load across the networks while also catering for different sensitivities of applications. For example, if an application can tolerate long latencies, schedule it on the more congested network, for example. If an application cannot tolerate long latencies, schedule it on the less congested network. So based on the network type and design and power, you can actually make decisions. I think it's very interesting, actually. There's more work that needs to be done in this area as well. Does that make sense? Okay, good. I'm going through a lot of ideas, as you can see, at a high level. We don't have time to cover all of them, clearly. I will cover some other ones, but if you have any questions, feel free to stop me. Now, let me go into packet scheduling element, because we have kind of looked at it, but kind of also not looked at it in the sense that it has a lot of other issues that we have not discussed over here. So basically, packet scheduling says, which packet do you choose for a given output port? There are some common strategies, and there could be better policies based. Router needs to prioritize between competing flits. So which input port do you choose? Which virtual channel within an input port do you choose? Which applications packet within that virtual channel do you choose? So there are basically many decisions that you need to make over here. Common strategies, as I said earlier, you can do round robin across virtual channels. You can do oldest packet first or an approximation of it, but we said that it's actually relatively complicated. So people actually couldn't do that as easily. Or you prioritize some virtual channels over others. Actually, oldest packet first is done, except the routers are very slow, basically. If you want to build a very high frequency router, oldest packet first doesn't work very well. But it's employed in real systems. There's also FIFO, first in, first out, actually. That's is not written over here. So in a multi-core environment, actually, a better policy should use application characteristics, as we will discuss. So this, again, goes back to thinking of the system as to accelerate the workloads, as opposed to thinking of the system so that you optimize some network level metrics. We really want to optimize for application and system level metrics. So I'm going to talk about a few ideas over here. So this is the packet scheduling, at least in the multi-core sense, right? You have a bunch of applications running on processors, and you have a network on chip that is enabling communication of those applications with the memory, as well as with each other, as well as with accelerators, for example. So essentially, it's a critical resource shared by multiple applications. And we've already seen this picture. The question is, what is done over here? So conceptually, what the router does is it basically takes packets from different applications. Different colors may be different applications over here, as you can see, and then schedules each. For a given output port, it decides which packet gets scheduled, right? So it's a complicated decision, clearly, as we have discussed. So existing scheduling policies are application unaware, basically. There are two issues, actually. One is application unawareness, which is problem 2. The other is actually localness. So this is actually interesting to think about. Golden flit, for example, makes the prioritization across the network consistent for a single flit. But if you actually have a FIFO or round robin or age-based Maybe age-based actually fixes some of the localness, but it still depends. It can lead to contradictory decision-making between routers. So packets from one application may be prioritized at one router to be delayed at next. This is true for oldest packet also, oldest first also, if you think about the application level. So on this router, in this router, you're prioritizing application A over application B. But this other router may be prioritizing application B over application A. So everybody gets delayed in the network in the end. Hopefully this makes sense, right? It's kind of similar to, at some level, it's similar to parallelism over batch scheduling, right? This bank prioritizes application A over application B. The other bank prioritizes application B over application A. As a result, no one exploits the bank level parallelism, right? This is kind of similar, except it's much more distributed. In each router, there could be a very different decision. As a result, different applications get deprioritized in every single router. As a result, everybody gets deprioritized overall. Basically, this is the downside of local, uncoordinated decisions across the network. One router prioritizes some application, the other router takes a complete different decision. As a result, both applications suffer. Okay. The second problem is application obliviousness. Essentially, these are application agnostic, right? As a result, they treat all applications equally. So they don't optimize for what we really want to do in a network, in a system, right? We want to really optimize for application level performance. But applications are heterogeneous, so you really need to take into account the heterogeneity. And you've already seen this many times in this course, right? Okay. So basically, the solution that this work proposes is more global scheduling policies that are application aware. So let's take a look at an example of a scheduling policy. So these are different cores. We're looking at it from a core perspective. And these are different injection cycles. And these are packet injection orders. So we're going to design a policy that actually uses batching and uses batching to coordinate across the routers. So again, every router follows a static batching schedule. And each core, or every core, I should say, every core follows a static batching schedule. So for time interval until here, for example, all of these are equal to the same batch. For the next time interval, you have another batch. So when you inject a packet into the network, you also inject the batch ID. This is from batch 0. And then these are from batch 1. These are from batch 2. So within a batch, you can do application-aware scheduling again. In a sense, it's again similar to parallelism over batch scheduling because there's some similarity in the router as well as the memory controller. So basically, within a batch, you can have a ranking order that says, if I prioritize this one, it actually has not much load, so it can actually go faster. And if I prioritize this one next, it can go faster than the red one. So there can be some priority order. Actually, it doesn't need to be as perfectly as shortest job first, as I kind of alluded to. It could be something else also, but we use kind of a variation of shortest job first in the router. Okay, so let's take a look at it. Basically, these are different batches. These are different requests, as you can see. Let's assume that they all arrived at this router magically. It's just for illustration purposes. And the router needs to make a decision as to whom to prioritize. It basically prioritizes. This is how the round robin would work. Basically, round robin goes through all virtual channels in a round robin manner. It takes the first one, second one, third one, and you can see that it's round robining. And then once you need the next packets, you go through the same routers, same virtual channels again, right? So basically, you can see that the order is really order of virtual channels. Okay, I'll go through this again. Okay, so if you think about applications getting delayed, and if you think about what we have discussed 10 lectures earlier, let's say, the stall cycles with round robin for the green application, basically green application's last packet gets delayed 8 time units, assuming these are equal time units, which they are actually. Blue application's last packet gets delayed until 6 time units, and the red one gets delayed until 11 time units. So basically, no one gets prioritized in this case, as you can see. And the average is about 8.3 over here. Let's take a look at what happens if you do age-based scheduling. If you do age-based scheduling, you pick the one that's the oldest. And these are marked in terms of the old one. So 1 goes first, 2 goes next. These are the ages, basically. Actually, these are the batches and ages, if you will. Let's assume that you break the ties based on some other age that's not shown here. So this is what you get. So stall cycles are still not good, as you can see. The average is 7.0. Now, if you actually impose some ranking such that you make a coordinated application-aware decision, and you decide to prioritize, for example, the green application first, and then the blue next, and then the red next, in this particular cooked up schedule, it looks pretty good, right? So you can see that the average stall cycles, the average time the last packet from a given application gets serviced is 5.0. So this picture may look similar to parallelism over batch scheduling. In that sense, it's similar actually, but the decisions are happening coordinated across different routers. In this router is prioritizing like this. The other router is also prioritizing like that, assuming these three applications happen to arrive at that router. So all of the routers are making a coordinated decision because the batching happens at regular intervals across all parts of across all cores. Hopefully that makes sense. So there's no real coordination that happens in a single place, right? The batching is happening at the cores when they inject the packets into the routers. Okay, so that's the key idea, basically. I mean, there's not a whole lot to discuss, except, of course, how do you make it work in a distributed fashion? How do you do the batching, etc.? How do you design the router so that it's not that complex? And those are all discussed in this work. And if you're interested, you can read more. But this is this work shows that application-aware prioritization actually is very important compared to these other mechanisms. So if you actually use application-unaware methods, like what's been used in real networks until then, and still I think in many networks today, you lose performance significantly. So if you think about this, bufferless routing that we've discussed so far is also application unaware, right? So you can combine the principles from here to here and there, but then you're complicating the router. So it's good to think about these things. Okay, there's another idea that I would like to also mention. This is actually very interesting, and this is a general idea again. So this work incorporates the notion of slack. And this notion is very important. We didn't discuss this as much, but we kind of alluded to it in some works. So there's this notion of packet slack, actually in general slack, request slack. Slack is the amount of time or the number of cycles you can delay a packet without affecting performance, or at least significantly affecting performance, or not affecting performance at all. This is also called local network slack in this particular paper. So why does this happen? Clearly, you can delay a packet one more cycle, and that's not going to hurt you. You can delay a packet maybe hundreds of more cycles, and it's not going to hurt you. Well, because you have some latency tolerance, right? We've discussed latency tolerance mechanisms. So it could be memory level parallelism. There's some other packet that's on the critical path of execution. And you delay this packet, it's not on the critical path, fine. Keep delaying it until it may become the critical path, basically. So that's the idea in slack-based mechanisms. Basically, the latency is hidden. I'm not going to read this again. But the key idea is, if you can somehow estimate the slack of a packet and prioritize packets with lower slack, you can get a much more efficient network, higher performance, as well as potentially lower energy, as this work shows. So that's the idea. Then the question becomes, how do you estimate the slack of a packet, right? And this idea is generally applicable, actually, to many things. People have tried to apply a version of this idea to processors. For example, if you can estimate which instruction is going to be critical on your critical path, prioritize that instruction in the instruction scheduler. Right? If you're memory controllers, for example, I mean, I don't believe actually there are some papers in memory controllers that kind of use this idea also. But basically, if you can estimate the slack of a memory request, prioritize the memory request that has the lowest slack in the memory controller. This is a notion of criticality in the end. And this work estimates the slack in multiple methods. So one way of estimating slack, if you're the source node, when you're injecting, you're kind of giving an indication to the network that, okay, I have a lot of slack on this packet, so you can delay it for some time. And here's the time I guess you can delay it for, maybe 100 cycles, right? How does the node estimate this? Well, node can estimate this if it knows where the packet is going, right? For example, one packet may be going to main memory, and you have that information somehow. Another packet may not be going to main memory. It can be serviced from a local cache, right? Or close by cache. And you may have some metadata information that helps you figure this out. And that enables you to actually guess how much slack a particular packet has, because in the end, the core will likely be bound by the packet that's going the furthest, that's going to take the longest, right? That's the idea. Of course, these are heuristics, right? It's not a complete exact mechanism. You may use heuristics to decide which packet is more important and how much slack does it have. This paper proposed a mechanism. By no means this is the best mechanism, but it is the best mechanism at the time. And I would recommend reading it because it's a very different notion than what we have discussed so far. And it also gives you a different idea of what it might enable. I believe this sort of policies are actually going to be a lot more important in systems. If you think about our systems, I mean, in a lot of the things that we have discussed here, we did not introduce this notion of slack, right? Or notion of criticality. Tomorrow's lecture, whether online or in person, we will see, it's going to be all about criticality. So in that sense, it's a good tie into tomorrow's lectures. Also a criticality in a very different sense. So our policies are actually quite inefficient because two things are not equal. One thing is a lot more important than the other one. The question is, how do you determine that thing is very important? In this particular case, it's about performance. You can actually say, okay, this based on, I mean, we kind of saw this in Rahul's lecture, if you remember the Hermes lecture. The Hermes work tried to predict which requests to the memory system are going to miss in the caches. And those requests are prefetched earlier, right? You could use that information to also prioritize requests. So this request is going to actually miss in the memory system based on my prediction. And I'm going to predict that it has little slack because of that reason, right? Everything else may have higher slack if you have concurrent requests, for example. So those sort of mechanisms can actually enable you to decide which requests have less slack versus more slack. Okay, enough on this one. There's a lot more that goes into actually making this work, and that's in the paper. Any questions? So there are a bunch of things that I'm not going to talk about. We don't have time. This is actually a very, very fun field. And you can do slowdown estimation in the network. It's much more complicated than slowdown estimation in a single memory controller. There are a lot of issues like multicast, hotspot. So there are a lot of issues in the network, basically. Let's keep it that way. There's quality of service. This paper we had discussed actually very, very briefly. This shows that you can do denial of service in the networks much worse than you do in the memory controllers that we discussed. But there's a solution also over here. Unfortunately, once you want to add quality of service, guaranteed delivery, or some sort of latency guarantees, routers become much more complicated as well. So if you look at the router and this work, and some other quality of service works, they're complicated. In fact, this work tries to make the router less complicated compared to some other past quality of service mechanisms. So how do you actually provide some latency bounds without complicating the router? That's still an important problem. And that's kind of a segue to what I'm going to talk about next. So I'm going to talk about this one later, but actually maybe I'll talk about it now, but I will introduce something else. So basically, the issue is, as you scale to thousands and thousands of nodes, router complexity matters even more because in the end, you're bound by design power in a chip. And if your routers are complex and energy hungry, then that's going to limit your scalability. And this is actually important on all kinds of systems. This work actually has authors from NVIDIA, and they're actually interested in scaling up their systems significantly. And that makes a big difference in the designs. So if you look at a GPU, for example, it has a very hefty interconnect today, so that you can connect all of those cores, of which there are many, many, to the memory downstream. And that is an interconnect, basically. So it's not, they cannot afford a crossbar in that interconnect, clearly. And they need some quality of service also. And if you look at a more complicated GPU, like an SoC, which it has not just the GPU, but it also has cores. Now those all feed into the interconnect. It's a common interconnect. Some of them may be sharing caches. So everything we discussed earlier in terms of memory controllers get amplified in the interconnect. Because it's not just a single memory controller or multiple memory controllers, it's everywhere. Basically shared resources everywhere now. And it has to be energy efficient, it has to be scalable, it has to be high performance, it has to provide quality of service on top of that. So this work tries to tackle a lot of those at the same time. I'm just going to give you some of the key ideas. Some of the other key ideas are low level, and you can read the paper if you're interested. But basically, as I mentioned earlier, the key realization is that we don't want to make the routers more complicated than they need to be, handle some of the problems in the topology. And that's actually a very interesting insight that we have never seen anywhere before. Handle some of the issues in the topology so that the router becomes less complicated. Okay, these are some pictures. So yeah, I think we're in this near future, actually. This work was published in 2012. Actually, it was done until 2011 or so. But we're actually very close to 1,000 agents. I didn't count clearly all the agents that we have, but if you think about GPU cores, we have a lot of GPU cores in a hefty GPU. If you look at the Cerebras engine, the machine learning accelerators, big machine learning accelerators that are wafer scale, they actually have thousands of processing elements. I don't actually remember the number. So we're there basically today. This work was done 10 years ago, so keep that in mind. So basically, you need everything, high efficiency, low area, low energy, good performance, and strong service guarantees, and a network that can support thousands of agents. Okay, basically the problem is quality of service support in each router is expensive because you need to buffer packets in general if you want to provide quality of service really well. You need to arbitrate, you need to bookkeep. Usually what's employed, at least the preemptive virtual clock, for example, the paper, it's a virtual time-based mechanism. You basically keep count of which flows have been serviced for how much, and you basically try to prioritize the flows that have not been serviced as much. This is a form of least attained service scheduling, for example. But that's not purely quality of service. That's trying to provide some sort of fairness, fair scheduling. If you really want to support quality of service, you need to have different traffic classes, maybe even latency guarantees. Like this is the latency that I've experienced so far, and I cannot afford more latency, so prioritize. So there's a lot of bookkeeping that you need to do. So quality of service can be actually defined in terms of latency, bandwidth, slowdown. There are many different definitions also. So basically, this complicates the router significantly if you need to handle everything in the router. And this paper actually covers a lot of those issues, which we don't have time to cover. So our goal, as I said, was to provide quality of service guarantees at low area and power cost. And the key idea is isolate the shared resources in a region of the network and support quality of service within that area. So basically, you minimize the amount of quality of service you have in the network. Some part you say, okay, this is lost cost. I have to provide quality of service here. So it's expensive over there. Now, how do you get to that part? Basically, you should not have interference. You should not have things that break quality of service in the other parts of the network. This is where the topology comes in. Design the topology so that applications can access the region without interference. This is where the earlier topologies that I showed you, low diameter topologies that provide direct access from one node to a shared region, enable you to do this nicely. So that's the idea. So in that sense, it's kind of a culmination of the ideas that we've been discussing so far. Okay, so let's take a look at this issue. So this is potentially a real system. It's a very small system, as you can see. I don't know why the color doesn't match, but shared resources are these, the blue ones over here. Somehow it happens to be that way. Multiple virtual machines are sharing a die over here. And then there's some VM virtual machine private resources. This belongs to virtual machine 1, for example. This belongs to virtual machine 2, for example. It gets divided over here. Virtual machine 3 is here. And some other virtual machine 1 parts are here. So somehow there's some allocation that happens. And virtual machines can get allocated multiple cores clearly, right? And all of these routers are quality of service enabled, as you can see. If virtual machine 1 may be communicating from here to here, right, somehow. And virtual machine 2, virtual machine 3 can be doing that also. So there could be many contention scenarios over here, right? You can have shared resources. You can have memory access, for example. So this virtual machine may want to access the memory over here. And then there could be another virtual machine trying to access memory over here. They contend all across the network, and quality of service mechanisms help both of them hopefully get quality of service. There could be, so we don't want that necessarily because we don't want quality of service everywhere in the routers, right? So how do you handle that? There could be intra-VM traffic also, and there could be inter-VM traffic that actually cause these problems. The paper details them, but we don't have time to go over all of these. But basically, there are many different scenarios in which you get, you rely on these quality of service aware routers across the network, right? So 2 virtual machines may be communicating with each other also, or communicating to memory. We will see that as well. So if 2 virtual machines, for example, share pages, how do they interact with each other? They have to go through basically, if virtual machines are allocated this way, and also shared resources are all over the place, and there's no, the network is designed in a way that there's a lot of interference to get to the shared resources and to enable the communication. You have to have quality of service in all of the routers in your network, basically. So we want to eliminate that. So we basically want, what we want to get is network-wide guarantees without network-wide quality of service support, if you think about it that way. And this is actually a worthy goal because these things are expensive in the end. Expensive in terms of not just cost, it's expensive in terms of energy as well as performance. So basically the insight is to leverage rich network connectivity, naturally reduce interference among different applications, flows, virtual machines, and limit the extent of hardware quality of service support. And this requires a low diameter topology. And actually, any low diameter topology would work over here. But we use multi-drop express channels because it's a low cost, low diameter topology. So let's take a look at this. This is a single dimension. You can see 1 row and 4 nodes. The idea of multi-drop express channels is essentially this. You have a single bus type of channel, and then you have multiple drops. It's a multi-drop bus basically. So you need to have some sort of small arbitration over here to decide this is destination. So you need to do ejection over here. So there's some buffering. So basically this is a low diameter topology because if you're sending from here to here, it just goes in a single link. There's no router in between. It's just a drop that you need to do. So there's this very small arbiter that to ensure that it drops at the right place. And you can see the design in the original HPCA paper. So basically it looks like this, multi-drop express channels. Yeah, this is a multi-drop bus, as you can see. And it looks like this internally. And then you keep adding it in all dimensions. And this is what you get in the end. Okay, so the router, I mean, inside here, you have a complicated router, of course, because you're receiving from 3 places over here and you're sending to 3 places. But you can, you're sending to 4 places. Well, assuming it's a torus in this particular case, of course. Okay, so if you read the MEX paper, there's actually very interesting pros and cons for different topologies, but this is a one-to-many topology. One of them gets connected to many, as you can see. It's low diameter, 2 hops. That's the important part. Some things I did not discuss, but you can look at it. So it's asymmetric, but there's some increased control complexity, but you can read the paper for more detail. So basically, we're going to use that sort of network. This is the topology of quality of service. This is the shared resource. These are the shared resources on the right. You dedicate the shared resources to be there. These are dedicated quality of service enablers. Here you have quality of service support in the routers, in the memory controllers, everywhere. But the rest of the die, you keep quality of service free, if you will. And now this is good, right? Now the problem is, if you want to reach this, you need to do something in the network over here, as we discussed, right? And that's where we actually have the richly connected multi-drop express channel topology, right? This virtual machine can directly reach here because there's a multi-drop bus over here. Similarly, this virtual machine can directly reach here. So both of the virtual machines at the same time can reach here because it's a multiple topology. You can see there's a channel over here and there's another channel from here. Right? So if this virtual machine from here wants to reach this quality of service node, it uses this link. If this virtual machine wants to reach this quality of service enabled router or shared resource, it uses this link. And they're completely independent of each other. So essentially they're interference free because of the design of the network. I glossed over some of the design issues in the network, but you need to read the paper for more detail of the multi-drop express channels. And again, as I said, there's nothing special about multi-drop express channels. We could have easily used a flattened butterfly network, for example, which has very similar properties to multi-drop express channels. The key is low diameter network and interference freeness in the dimensions where you need the interference freeness. And here we satisfy that. So, okay, virtual machine 1 wants to communicate with virtual machine 1 parts over here. How do you do that? Well, unfortunately, this topology is not good enough to support that. To be able to support that with topology, you need to have a direct link from here to here, which is very tough. Or you need to have a direct channel that's dedicated. But that's also very tough. So now the traffic, the intra-VM traffic that's green in VM2 can contend with intra-VM traffic that's red over here. So clearly there's contention because they have to go through the same link. Make sense? Because it needs to take a turn over here. Even though this link is different from this link, there's no interference between these two over here. There is interference between these two because they need to use the same link to get to the to these two destinations. Of course, if you're completely richly connected, maybe you could avoid that also, but that's a very expensive topology. But in this case, what we do is this. You have special routing rules to manage interference. So now actually, not only topology, but routing is modified to manage the interference so that we avoid quality of service mechanisms here. Okay, what are those special routing rules? Well, if you want to take a turn so that you get connected to some other part of the network, which you need to get connected to by taking a turn, take that turn in the quality of service enabled region. That's the idea. So this way, virtual machine 1, because of the way things get allocated, it knows that it has to go through some other virtual machine space So it has to go through, if it wants to be interference-free and have quality of service, it needs to first send the message to the quality of service aware router, which sends the message to its other piece in the network. So hopefully this kind of clarifies what's going on, right? Virtual machine 2 can use its own internal connectivity over here because the information is such that it knows that these resources are allocated to itself and can freely communicate internally without interference with anyone else. But other virtual machines that are separated, if you will, in terms of their resources, they have to first go to the quality of service enabled region, and then from the quality of service enabled region to the destination piece of the virtual machine, if you will. Now, this is interesting because now we're actually trying to solve the quality of service problem, not by throwing quality of service to each router, but designing a topology that minimizes interference, which it does in some cases. But when it doesn't work, design the routing algorithm to avoid the interference, or at least avoid the certainly avoid the interference, but also go through the quality of service enabled region to get quality of service. So this is an example where you can combine all of these, everything we've learned so far, topology, routing, flow control, and quality of service, even though we didn't talk a lot about quality of service over here, to actually get to a solution that is much more scalable as the paper shows. Okay, so I think I've already discussed this. There's a bunch of other stuff that the paper does that I'm not going to go into, but you can actually optimize the flow control. If you're careful about what's going on over here, you can design a flow control mechanism that reduces the buffer requirements in these regions. It doesn't go all the way to deflection and bufferless routing, but it reduces the buffering, and that actually helps the energy efficiency and scalability. And the paper does a bunch of evaluation, and I'm not going to go through this, but basically the area of this is much lower than prior mechanisms. This is basically multi-drop express channels with some quality of service and support in every router. This is the final kilo-NOC design. And you can see that the area is almost half because you get rid of the quality of service support in the routers, and you also do optimize a bunch of buffering in the routers. This is energy, as you can see, and these are different intermediate stages that I'm not going to talk about. This is quality of service support in every router plus mix, and this is kilo-NOC, as we have discussed. You can see that the energy is much lower, and there's also, based on the traffic pattern, you can also see. Okay, so there are multiple principles that we kind of discussed. Just to put this back, it's in the end, it's a heterogeneous substrate, right? Not all routers are the same. Some routers are quality of service capable, and topology helps quality of service because it enables you to limit quality of service support to some routers by leveraging these low diameter topologies. It also improves network on chip area, as we discussed. I didn't show. Well, I guess I showed energy efficiency, but it doesn't impact performance significantly while providing strong service guarantees. Again, those evaluations are in the paper. We don't have time for that. Any questions? I kind of distilled a lot out of a very complicated design for you with the key ideas. But if you read the paper, you will see a lot more complicated things to do to provide quality of service, actually. And if you really don't want to read the details of it, this is a shorter version. And that shorter version is a lot more, let's say, watered down in terms of the detail. Okay, but in the end, it builds on some sort of network like multi-drop express channels. So these express channels are important because it enables express connectivity from one region of the network to another region. This is not the first paper on express channels, clearly, but it's a specific papers on express topologies. It also provides a formalization of different express cube topologies. These are called express cube topologies in general. Basically, whenever you have express channels from one side of the network to another side of the network, and you do have to have them if you want to have a low diameter in a network, it's called an express cube topology. And if you want to read more about the formalization of it, you should definitely take a look at this paper. There are old papers that actually build a theory of interconnects, like Bill Daly's papers. Bill Daly is one of the authors of the book that I mentioned. And this paper actually advances that theory a little bit also. So there's a theoretical contribution as well if you're interested in that. Normally, I don't look at theory a lot, but there's some theory that you can develop over here. It breaks down when you actually feed applications to it. When you actually feed applications, that theory is nice, but it's very hard to predict the performance of a network because it's all dependent on the application patterns. Okay, that brings me to the end of this lecture. There's actually more to cover, but I didn't expect it to cover it because, so I put it in backup slides. So if you're interested in more, there's some more in the backup slides. But I will say that this is actually a really important area that people need to focus on with a different mindset going into the future, because this is a very important part of the communication substrate, not just on chip networks, but interconnects in general. In general, I think we need to focus more on that. In the research community, unfortunately, there is not as much focus, but in the end, I think this will come back. There was a lot of focus, let's say 2000, 2009, 2010 area. And then, yeah, there was less focus, let's say. People focused a lot on memory. Memory is important, clearly, but this doesn't mean that interconnect is not important. So there's less focus, unfortunately, in the research community. That means that maybe a good idea to actually develop big ideas right now so that it can have a lot of impact going into the future. So the fact that research community is not examining something doesn't mean that it's not important, basically. Or the community that is not examining something in general. We saw that in systolic arrays. That's one of my favorite examples. Systolic arrays have not been examined for such a long time, but people figured out that systolic arrays are actually very useful for machine learning accelerators, for example. Okay, I will stop here. Any questions? Yes, please.
During the lecture, you talk about many mini optimization skills, as you also mentioned local to the routers. But I was wondering if you have this global to the whole networking optimizing, like this memory controller. Maybe we can also, because I think each router have a limited choice for routing, and the topology is also fixed. It's not like changing through different tasks. Yeah. So maybe we can simulate what's going to happen given every time, every minute you have a new task, and given what's already simulated of the previous task into the future, you re-simulate in the future what's going to happen. And maybe in the simulator, you are able to find out where is the congestion or where the biggest traffic are. And then you make some new plans according to what's going to happen. Yeah. So it's a little bit more like global adaptive simulator.
Yeah, I absolutely agree. I think, I mean, there are some things that I did not discuss, like global policies. You have a global controller, for example, that tries to figure out the congestion and basically tries to map the tasks differently so that you reduce the congestion either during execution or in the next execution. Yeah, certainly there are works that are, this is a huge field, so there are works like that. But I agree that I think that sort of information is also important.
Yeah, but I was wondering like how this simulator could be implemented in the hardware. As in software, we have compiler. Maybe this has also like router compiler to router scheduler to really plan for every step for the router.
I see. Yeah, I mean, that's why do you want to implement it in hardware? Why not in some sort of operating system scheduler, perhaps, right?
I guess because network is very basic, basic fundamental devices for SoC. So if you put things on software, it becomes slower.
Oh yeah, certainly. Yeah, I mean that's part of a research direction, I would say. Basically, how do you figure out what will happen in the future based on some simulation, and then adapt your policies? Yeah, I mean there will be some hardware cost clearly to predict what will happen in the future if you want to simulate. And simulation may not be perfect also, right? Because it could be expensive. Yeah. Yeah, but I mean, these sort of policies are certainly interesting. I mean, there are many applications of it. For example, if you see some parts are really congested and you expect that it's going to be congested, you may remap the application a different way, right? For example, you may remap the virtual machines over here in a complete different way, right? So certainly those things can be employed.
It's like a memory controller trying to optimize the best performance among different memories, and then this is like a global router controller to reach the maximum.
Yeah, that makes sense, I think. And on chip, you have actually a lot more possibility for that, because on chip, yes, chips are getting bigger today. It's becoming more difficult, but comparatively to the huge distributed system on chip, you have a lot more possibility for global controls.
Definitely, yeah.
Okay, any other questions? I think we're on time anyway, so